Now we'll start on with the foundations of AI, machine learning, deep learning, what these different components actually are. So let us start on with the foundations of what is AI, what is ML, what is DL, and pretty much we'll try to deconstruct all the different jargons that we have in this particular field. So it all started in 1950s. 1950s was the year when the term artificial intelligence was first coined. And apparently there was a Dartmouth conference that happened. And in that Dartmouth conference, all the researchers in the field, they came together and the domain of AI was proposed. And the whole inspiration was, how do we make machines think and act the way humans do? That is the whole inspiration behind coining the term AI or artificial intelligence. Make humans, how do we make machines think and act the way humans do? It was a big thing around that time because remember 1950s was an era where we had nothing. We didn't have computing devices back then. We didn't have a lot of the things that we take for granted. We didn't have those devices back then. It was a very new idea. So the world's very first computer was ENIAC. It was a room-sized computer. So it came around that time. It came around the 1950s. So there were no programming languages, right? Where you write a script, you give a computer instructions to do certain things, and the machine does it for you. There were no programming languages back that time. All that started coming a lot later. So the idea of AI, even the simplest forms of AI, were very new around that time. That how do we make a machine think and act the way humans do? So if a human being is doing a particular task, can I program that into a machine? Can I program the logic into a machine, into a system, or into a computer as we call it today? And that computer will repetitively perform those instructions exactly how we asked it to do it. And this is what led to a specific branch of AI, which is what we refer to as rule-based AI. All of you can see my screen. This is what we refer to as rule-based intelligence, or what we call rule-based AI. That is rule-based AI. So rule-based AI is that kind of AI where you tell the machine what to do and how to do it. You explicitly define the rules. You explicitly define the logic, and you tell the machine explicitly what you do, what you want it to do. I'll give you a very simple example of rule-based AI. Imagine you have your home air conditioner that is on right now, and it is running at 26, 27 degrees Celsius. Let's say your home air conditioner is running at 26, 27 degrees Celsius, 27 degrees Celsius. It is set to auto mode. So what will happen? There is a sensor in the air conditioner that is constantly monitoring your room temperature. If the temperature of your room falls below 26, the AC will stop cooling. Sometimes you hear the compressor stops. When the room gets too cold, the compressor stops. And if your room temperature increases above 26, the compressor automatically starts. No? You will see the fans are whirring, and you'll hear the sound of the AC. Sometimes it stops, sometimes it starts, sometimes it slows down. Right? We have variable compressors also. So what is it? Think about it. It's a kind of an intelligent machine, right? It's a very basic example, but that is how AI came to be in the 1950s. That is how, and that is the inspiration with which this idea was coined. That instead of having a human being control the temperature manually, can I program a set of rules, or can I program an if-else statement? It's like a if-else conditional statement, right? So if the temperature is greater than this, then this will happen, else this will happen. If the temperature is more than the room temperature, right? If the room temperature is more, then the compressor will start, else the compressor will stop. So this is how we think of a rule-based intelligence system, where the rules are predefined. You study the system in detail, you provide the rules, you hard code the rules, and you explicitly tell the machine what to do and what not to do. And this is also how we do traditional programming, right? When you write a computer program, when you write a software, what are you actually doing? A lot of you are software developers. And whenever you write a software program, whenever you write a computer program or a script, what you are doing is exactly this. in a way, you're doing exactly this. You're giving a set of rules and you're telling the machine what to do and how to do it, isn't it? You study the instruction, you study the system specifications, and you explicitly design the set of rules. You say, okay, if this, then we will do this, else we will do this, right? So you study the system design document and you say, okay, if these conditions are true, then we will do this, else we will do this. Let's say you're creating a web, a front end web application, right? A full stack application you're trying to create. So full stack, there is a front end, there is a back end. So the front end, you will write a specific set of rules to make the front end of the website behave exactly the way you want, right? So if you click on the button, this will happen. A button click event will be triggered. You write some JavaScript, right? All of you would have heard of HTML. It's a markup language. So you can design everything, every aspect of the website, right? So you can decide the background color, you can design the text, the formatting, the layout, and everything. So if you think about it, it's rule-based intelligence. It is not that the website is itself deciding how it should look like, but that has been hard coded. If you go to wikipedia.com, Wikipedia looks the same for you, it looks the same for me. Wikipedia has the same look and feel for everybody, right? And even if you look at backend programming, the backend development, which we do with Express.js, Node.js, and all that, even the ideas are very, very similar. You have explicitly hard coded what will happen. If you click on a button, something specific will be pulled from a backend database and it will be returned to you. Okay, let's say you're entering a form information. You're giving your username, password, and you click on submit. Something is happening. Okay, some information is getting pulled from the backend. So all that is design, all that is static thing. Okay, even inside the organization, if you're trying to design any applications, you will write the rules, you will write the code manually. There are tons of applications we see around us. Let's say we are all having mobile phones. Okay, we are all having mobile phones, and uh, the workings of the mobile phone are governed by the operating system, the OS. You might have an Android OS or an iOS, whatever. Okay. Now, very interesting. If you keep your mobile phone in the sun for a long time, okay, so let's say in peak summer, in peak afternoon, you go out in the sun, you go to the terrace or go outside your office, and you keep your mobile phone directly under the sunlight for 5-10 minutes. You'll be surprised to see that after a while it gives a thermal heat warning. Okay, the mobile phone will actually stop functioning, and this is a feature that is built into the operating system. Because think about it, what is the operating system? The operating system is effectively a set of instructions. It's nothing but software, it's code. It's like hundreds of thousands of lines of code that are written, which govern how our smartphones are going to work, right? Everything from resource management, memory management, to even something as simple as battery saver. If your mobile phone goes below 15% battery, what happens? The battery saver mode is automatically enabled. And as part of the battery saver mode, you would have observed that the brightness of the device dims. And also, as part of the battery saver mode, the camera application, the flash does not work. So these are some of the things that happen whenever we start the battery saver mode. So the background typically dims, and also the flash of the camera application typically doesn't work. So these have already been hard coded into the system. And there are many, many other applications. You can think of the laptops where you're attending the session or you're listening to the video right now that we are in. And if you look at the functioning of the laptop, laptops also are governed by an operating system. And that is again a set of hard-coded rules. It is a set of if-else instructions that are governing exactly how the laptop will function under different circumstances. So if it goes out of battery, what will happen? If it goes to low battery, what will happen? Because sometimes when your laptop goes to low battery, you will see all your sync applications will stop. If you have OneDrive, if you have Google Drive, all those desktop sync applications will stop. Okay, so many of the background data tasks will automatically stop. Okay, even something as simple as not responding. Sometimes when you start a very powerful application in your laptop and your laptop doesn't have enough memory, you will oftentimes see that some of those very high memory consuming apps will go to not responding mode. So who is controlling that? Who is controlling that how much resources should be allocated to the different applications? All this is governed by static rules. Okay, static rules that we have hard coded, right? Now, and you can see countless examples around you. Okay, so if you have a car and if you go to your vehicle, the modern day automobiles have many of these so-called static or rule-based AI components. Seat belt, if you don't put the seat belt, there's a seat belt alarm that will go, right? What is a seatbelt alarm? It's like a simple if-else statement that has been hard-coded into the car. If it detects the seatbelt is there, fine. If it detects the seatbelt is not there, the alarm will start to beep. Okay, so it is like if seat belt, then no alarm. If no seat belt, then an alarm will start to beep. So that is how we can think of a seat belt alarm. Well, automatic headlights. If it detects that there is no light, the headlights will automatically come on. If it detects rain, automatically the wipers will come on, right? Or sometimes there is also automatic central locking. So you just come to the car, you start driving the car for 50, 100 meters 50 meters, you start driving the car, and automatically the central locking will be done. And if you think of all these use cases, or maybe in the office spaces, you will have motion sensor based lights. Okay, so if there is nobody in the office, the lights will go off. And once you start entering the office, it will detect your movement and the lights will come on. Okay, and if it doesn't detect movement, the lights will come off. Or even something as simple as a revolving door or an automatic entry exit door that you see in office spaces, right? So if it detects motion, if the sensors will detect somebody is coming, the doors will open and otherwise the doors will close. There is no rocket science in any of these applications if you think about it. If you think about any of these applications, they seem incredible. We take it for granted because they're a part of our day-to-day lives, right? We see a opening and closing of doors all day long. We are in office. But if you think about it, it's a pretty incredible system. So somebody has programmed it. Somebody has programmed how that motion sensor light is going to work. It's a computer program, and it is rule-based AI. The rules are hard-coded, and it is a simple if-else statement. It's a simple if-else conditional statement. If this, then I will do this, else I will do this. Somebody had to give that. Somebody had to give all those explicit conditions. Even something as simple as a coffee machine. You go to the coffee machine and you hit latte, something will happen. You press cappuccino, something will happen. Think about it. Isn't it incredible? Isn't it incredible that when you hit cappuccino, the machine understands how much of milk to add, how much of coffee to add, how much of frothing to do? Because typically cappuccinos have more frothing. No, I mean the frothing cycle is longer. Whereas if you do latte, it understands what happens in latte. Whereas if you do espresso, no milk is added. Isn't that incredible? Now, again, we take it for granted because it's part of day-to-day life and work that we do. But you press a button and the machine somehow knows, the agent somehow has the intelligence what it has to do. You go to your home and you will have to wash your clothes tomorrow. Let's say you go to your washing machine, put all of it in, and you hit a button called summer mode. I don't know, I'm just making it up. There's something called summer mode, let's say, or um, there is something called outdoor mode. All the top end machines come with different modes, right? You've got something called outdoor mode, sportswear, cotton mode, delicate mode, synthetic mode, steam mode. What is it? What is it? So you press a button and the machine magically understands what it has to do. How? How does it know that? Because the rules are hard coded. When you designed, the manufacturers of the washing machine have already hard coded the rules in terms of what they are supposed to do and what they aren't supposed to do. So if it is a cotton mode, the entire cycle is hard coded. That how much is the wash cycle, how much is the rinse cycle, how much detergent has to be taken, how much fabric conditioner has to be taken at the end of it. Everything is pre-programmed. You go to a assembly plant today, a typical manufacturing plant where you're manufacturing different automobiles, different types of products. Even a simple bottling plant, a water bottling plant where water bottles are manufactured, there are machines you see all around you, right? And when you look at each of these machines, which are performing very intricate tasks, even something simple as sealing a cap is quite incredible, isn't it? When you have a water bottle and you see that machine that is actually automatically sealing the cap and sealing that cola bottle, it's an incredible process. But can you think about who designed that machine? What is that machine doing? Is that machine able to figure out by itself how to do that task? No, it has been pre-programmed. And that's the way how we think of the term rule-based intelligence. But I want you to know one thing, that this is how AI evolved. This is how AI grew long back. Even today, we have a lot of devices which are based on static rules, but there are limitations. But there are limitations. And now we will talk a little bit about what those limitations are. Okay, so any kind of traditional software, you see the things around you today, a lot of it you can relate to as rule-based intelligence. There is no machine learning that is going on here. It's just simple intelligence. It's simple artificial intelligence that we have hard coded. But there are limitations. Now, what are those limitations? What are the limitations of rule-based intelligence? What if the rules are not known? What if you're dealing with applications, especially in the world of unstructured data? When I say unstructured data, I mean to say images, audio, video, text, all this kind of data. Especially when we start discussing about unstructured data, what if the rules are unknown? What do you do in that case when the rules are not known, when we don't even know what the rules are? What do we do in that kind of a situation? Because now we cannot design an if-else statement, right? So what do I mean by this? What do I mean by this term that the rules are not known? So the best way to explain this, let me open up my photos, and I'm going to just take up a small example to highlight to you what I mean to say when I say that the rules are explicitly not defined. Let us see that for a minute. In the meantime, I'll bring up a small example for all of you here as well. So imagine that you have a task where you need to go through a picture, an image, and you have to predict what this picture is, right? So let's say that's the task that we have. You have to go through this image and you have to predict what you see. I'm sure everybody in the class understands that this is called an elephant, right? All of you know that it's called an elephant. Now the thing is, how do you know if you're trying to build an image classification model? How do you know, or what rules did you use in your mind to say that this is an elephant? How do you know, or what rules do you use in your mind to say that this is an elephant? So you can think of a series of rules, right? You can say that, hey, if I see if I see one trunk, two tusks, four legs, one big body, two eyes, then elephant, else not elephant. We can think about it from that perspective. We can think of that series of rules. If I see all these different things working in tandem, then it is an elephant, else it is not an elephant. But if you think about it, these rules are extremely hard. These rules are extremely hard. I mean, these rules work fine for the first elephant, but the rules do not work fine for the elephant at the back. Because if you think of this guy at the standing at the back somewhere here, the rules do not apply for this elephant, this other elephant. Why? Because for the elephant at the back, we cannot even see the legs. We cannot see the tail. We cannot see the eyes, ears, nothing. Right? And let me make it a little bit more complicated. Okay. So it's so difficult to hard code rules in these kinds of scenarios. If you look at this one, look at this. The tusk is such a defining feature of an elephant, right? But can you program it? Can you explicitly program and say that if there are two tusks, it's an elephant, else it is not an elephant? Can you pre-program the instruction? Actually, you cannot. You cannot explicitly hard code the instruction. Why? Because if you see the elephant at the back, this elephant has a single tusk. The first one on the foreground has two tusks, but the elephant at the back has a single tusk. And to make it even more difficult, look at this one. Look at this example. Look at this one. I don't think there's absolutely any doubt that this little elephant, this little guy here is an elephant, right? But there is no tusk. So if you think about it, images can be extremely complex. Even something which has a very defined structure like elephants, we all know what elephants look like, but we cannot hard code, we cannot write a script to identify elephants. That is what I'm getting at. We cannot explicitly write a script and where we say, hey, you know what, this qualifies as an elephant and this does not qualify as an elephant. Writing that script is impossible and very difficult. And look at these guys at the back. What script do I write for this one? I'm sure you're pretty certain that it's an elephant, right? I don't think there's any doubt about it. But even if you look at the pixels of the image, there is nothing that tells you that this is an elephant. There is no eyes, ears, nose, nothing. There are no legs. So even if you manage to write an if-else statement, it will completely fail at detecting these kinds of objects. So in the real world, whenever you're working with unstructured data like images, audio, video, text, data which is complex, which cannot be defined or designed using simple rules, these kinds of data, we cannot write rules. We cannot use rule-based intelligence. And it is for this reason that we need something else called machine learning, right? So what happens when the rules are hard, right? So here we talked about elephants. Elephants are still easy. They're still comparatively easy, right? But what if instead of elephants, now we are discussing about some other kinds of objects? What if instead of elephants, I ask you to now identify some other kinds of objects? Let's say, for example, mountains. Think about it. How do you write a piece of code to identify mountains? It is extremely difficult to do, right? How do you write a piece of code to identify mountains? Very difficult to do. It is very difficult to write a single piece of code to identify mountains because mountains can take different shapes and forms and colors, right? Mountains can be brown, mountains can be green, mountains can be um, it can be white. If you go to a snow side area, it can be white. So there can be different ways how mountains can look like. Mountains can take different shapes. So elephant still was something we could potentially do. But the moment you relate it to more complex objects, they become increasingly more and more difficult. So it is very difficult to classify and write code for mountains. If I want to identify mountains, I cannot write the rules. There's no way I can write a single set of rules to identify mountains. And if you think about it, the same also applies for other forms of unstructured data. So next time you go to a Google Assistant, and it's not new. Obviously, now the assistant has been named to Gemini. But even if you go years back, Google started with that microphone button years back, long time back. It's not even like long time back, even before OpenAI existed as a company. So Google had that microphone button, right? You can say, okay, Google, and it will do things for you. What is it? What is that doing? Every time you use that particular phrase, or every time you say, okay, Google, so microphone will actually fire up. Every time you say, okay, Google, a series of things will start happening. Every time you say, okay, Google, a series of things will start happening. So first, Google has to recognize it is you who is talking. And imagine how complex that would be. Imagine how difficult it would be to do that. It would be very difficult to recognize that it is exactly you who is talking. So recognizing that would be very difficult to do. You cannot write a set of rules. You cannot say, okay, if this, then it is Cheyenne. If this, it is not Cheyenne. If this, it is Roshan, else it is not Roshan. It's very difficult. And it is very difficult to hard code audio data into specific words. Because every time I say something, the manner in which I say it will be different. Every time you say something, there is a very unique way that you will say it, right? Because even audio data, whatever you say, your speech can be encoded in numbers. So every time you say something, you are using a different pitch, a different frequency, a different voice modulation, a different tone. So the tone is very different, and it's very hard to write rules in these kinds of cases, right? I hope everybody at this point in time understands that there are many applications we see in the real world today, which are simple circuits, which are simple rules, simple if then else instructions. At the same time, there are many applications we have today where writing these simple rules are not only difficult, but they are impossible. You cannot even fathom what these rules potentially could be. We don't know what these rules will be. And that is what led to the growth of machine learning based AI. So here also we are designing intelligent machines. Here also we are designing intelligent systems. We are making machines intelligent, but not using static rules, using machine learning. So when the rules are hard, what do? We give the machine lots and lots of data. We give the machine lots and lots of data, which are nothing but input output combinations. Okay, we give the machine lots and lots of data, and we let the machine figure out the rules. We do not hard code the rules ourselves manually. We don't hard code the rules manually ourselves, but we let the machine figure out the rules instead. And that is what is referred to as machine learning. And as you can see, it is more dynamic, unlike rule-based intelligence, which was static because we are pre-programming, we're writing the code, right? It's static. Machine learning is dynamic because the rules are learned by the machine, and it is also much more prone to mistakes. So unlike static rule-based intelligence, if you see in machine learning, it's more dynamic, and it is also error prone. It's prone to more mistakes and it's prone to more errors because it can happen that the machine ends up learning the wrong set of rules. To help you understand this idea a little better, you can think of a very simple analogy of how a kid learns, of how humans learn. Humans also learn from lots and lots of examples, right? If you think of a typical human being, human beings also learn from lots and lots of examples. So machines also learn from lots and lots of data or lots and lots of examples. So give the machine lots and lots of data, input output combinations. Teach the machine just like how you teach a small kid that, hey, okay, if this is the input, this is the output. If this is the input, this is the output. Just teach the machine the same way that you will teach a small kid. So if the input is this, the output is this. The input is this, the output is this. The input is this, the output is this. Give lots and lots of these input output combinations. And based on that, the machine will use some algorithm. It will build a mathematical model. And then using that mathematical model, it will do the predictions. So this diagram gives a very, very basic picture in terms of how machine learning actually happens in the real world. So you can see here that we are not giving any static rules. We are not hard coding the rules. Rather, we are giving the machine lots and lots of input output combinations. So we are giving the machine lots and lots of XY combinations, XY, XY, XY. You can see 1, 2, 3, 4, 5, 6, 7, 8. So we are giving the machine lots and lots of these so-called input output combinations. And this is called the training data. So what is this entire thing called? This entire thing is called the training data. So the machine is getting trained on the training data. Okay. So you have the training data, the data that is having the input output combinations 1, 2, 3, 4, 5, 6, 7, 8. You have the training data, and we will use some algorithm. And based on that algorithm, we will build a mathematical model. The mathematical model is nothing but the rules of the function. So, and the rules of the function that we are learning right now is y equal to x plus 1. So this is the rules and the function that we have. So based on the data x, y combinations, we use some algorithm. And based on that algorithm, we learn the model. And the model that we end up learning here is y equal to x plus 1. That is learned. Okay, so this is the biggest difference between the classic rule-based AI that I explained so far and machine learning, because in machine learning, what is happening is this equation is learned. This equation is not something that we are providing initially, but this equation is something that the machine is learning from the historical data. So based on whatever patterns I'm showing it, based on whatever initial data patterns I'm showing it, the machine is able to figure out this relationship. The machine is able to figure out this association between the x and the y. It is able to figure it out. It is able to figure out the association between the input and the output. And once it understands the association, so based on the data, using the algorithm, once it figures out the association, once it builds the model or the rules, once it figures it out, that is called model fit. That process, that part of the process is what we call training, model training, or fitting a model. So oftentimes in machine learning, as we go through the remaining discussions, we will oftentimes use a term called model training or fitting a model. So what is the meaning of fitting a model? What do you mean by model fit? This is what is model fit. Okay, you have the data, you will use some algorithm, and you will train the model, or you will fit the model. And the next part is, once you have learned the equation, once you have learned the rules, using that you will do a prediction. That is what we call model.predict. So there are two parts to the equation. The first part is we use the data and we do a fit. We create an equation. And the second part is based on the equation, we do a dot predict and get the predicted value. So these are the two parts of the equation that we have here. Now, to summarize it further, this is how it looks like. And as we go through the remainder of our discussions, we will actually see in hands-on how this can be done. So how we can use different types of data, and how we can use different types of algorithms, and how we can actually build different models. Okay, how we can basically have the machine learn the rules. And that is the biggest advantage, because real world data is so complex, even for seemingly unstructured forms of data, if you look at images and audio, video, text, especially the examples I was taking, they are so difficult that it is very hard to write the rules. So just give the machine lots of examples and let the machine figure out those rules. Let the machine figure out what the associations will be. And that is the biggest benefit of machine learning. But as you can imagine, sometimes the machines will not do the right job. Sometimes the machine will not learn the rules properly, and whenever the machine makes those mistakes, we get errors. Okay, so that is a part and parcel of machine learning that we have to accept. Okay, so sometimes we have to accept that machines will make a mistakes, machines will do a poor job, and when that happens, whenever the machines do a poor job, whenever the machines make a mistake, we have to accept that that is when we have to we have to accept that that is when we see mistakes happening. So sometimes you will see a picture is not classified correctly. Sometimes you in the voice assistant you will say something, but the model will hear something else, and that is the same reason why when you type something sometimes wrong responses come. Okay, because the rules are not correctly learned. So another very nice way to think of machine learning would be this example. This is the example I typically like to take so that you can connect the dots better. And as I said, one of the best ways to think of machine learning is how a human learns, how a kid learns. Okay, so how does a human being learn? How does a kid learn in kindergarten? Okay, so let's say it's your first day in school, it's your first day in kindergarten. How do you learn? How do you study something? How do you figure out something? Okay, so somebody has to teach you, right? Somebody has to teach you what is an apple, what is a banana, what is a watermelon. Somebody has to show you lots and lots of example data, and somebody has to teach you that okay, pictures like this are mango, pictures like this are banana, pictures like this are watermelon, and so on and so forth. So somebody has to give you the data, and somebody has to explicitly teach you that okay, I show you a fruit. So that is what you do to a kid also, right? You show the kid examples of fruits. You show them and you tell them, okay, these are what we call apples. This is the input and this is the output. You show them another fruit and you say, okay, you know what? This is a fruit, how it looks like. So you see the size of the fruit, the shape of the fruit, the color of the fruit. All these are the inputs, right? So you're showing the fruit and you're telling the kid, okay, this is the fruit I'm showing you right now. You please observe the fruit carefully, observe its attributes, and then you're telling, okay, this is called a guava. This is the output. So see how humans learn, how young kids learn, they learn the same way. So, okay, otherwise, if you don't teach the kid properly, the kid has no way of knowing that this is an apple or this is a guava. So now you're showing lots and lots of examples to the kid. You're giving lots and lots of examples. You're showing the picture of the fruit and you're telling it what the fruit is called. You're showing the picture of the fruit and you're telling what the fruit is called. And it is through those examples that now the kid understands that, okay, this is actually called a guava. And that's the core and that's the crux of what we are trying to do in machine learning. Okay, we have the machine is learning, and in this case, the kid is learning from the historical data. And once it learns the patterns, once you have taught it well, once you have taught it, apples and guavas, now it has a model. And now if you show it a new kind of fruit, the kid will know what that fruit is called. Okay, so if you show it a new kind of fruit, the kid will be able to predict between those two varieties what it is called. Remember, it will only be able to predict from the two varieties. It cannot estimate some other kind of fruit. Let's say you haven't taught it some other fruit like a watermelon. The kid will not know what a watermelon is because you have never taught it. Okay, so the kid's knowledge or the kid's model is only limited to what you have taught it, only limited to the training data. And that is why in machine learning, as we get deeper into building models and other things, we will discuss this topic in detail. That it's very important in machine learning that we decide, that we figure out what is the overall uh, what is the overall quality of the data. The quota will dictate a lot of things. Okay, so having the right data quality is very, very important. Okay, so having the right data quality is very, very important in the larger scheme of things. Okay, because if your data is not right, if you're not training the kid properly with the right data, the model that ends up getting built is also not right. Okay, and just to show you, just to give you a couple of examples, with respect to this particular thought, there have been some very interesting mistakes that machine learning has done, right? So there have been some very, very interesting uh, mistakes that machine learning has done over the years. And one of these mistakes I wanted to share with you was this one, where Google actually misclassified a black person to be a gorilla. This was long back. This was in 2015. Okay, but it was a blunder that Google made. So what happened was, this is how the story goes. There was a person named Jackie Alsine, and he took a selfie with his friend, and Google and they used a Google Lens to see the picture. And what happened was the Photos app, because Photos was very new around that time. Today, Google Photos is very good. This was 10 years back. And the Google Photos app mistakenly labeled a black couple as gorillas. Now, if you think about it, this is classification, right? It's classification. But if you think about it, what went wrong? What actually went wrong? What went wrong was because the data was wrongly labeled. Okay, so the original model, because Photos was a very new application that time in Google's repository. So whatever data they used to train the model was incorrect. Okay, so otherwise it does a lot of things right. But if you see, these are all the pictures that they took, right? And all of them were labeled as gorillas. So later when they went and went to the Photos application, just like you use Photos.google, and they search for gorillas, they found their pictures. This is model prediction happening. So what you're seeing right now is uh, this is like model prediction happening, because that's how that's how in a way the data was trained. And if you think about it very clearly, even Google kind of acknowledge the sensitivity, and they say genuinely sorry and there's a lot of work to be done, all that. And you can see we are taking immediate action to prevent this type of result from appearing. And what is the action they have taken? And this action exists even today, right? This action exists even today. If you go to the Google Gorillas application, sorry, if you go to the Google application and if you type gorilla, okay, if you search for the gorilla keyword, the gorilla keyword actually doesn't appear, so it was such a sensitive mistake that even today, if I go to my Google Photos and if I search gorilla, you can see gorilla doesn't appear. Okay, because I mean, Google doesn't want to risk it again. They don't want another black person to be misclassified as a gorilla. And if you think about it conceptually, what is really going on, based on some of the foundations that we covered until now, conceptually we have some X and we have some Y. As I told you, machine learning is that form of intelligence where the data has to be trained, the model has to be trained. You have to show it lots of input output combinations. So input is like the picture, input is like the original image, right? And output is like the label. What is the label? What is the class? What is it actually called? So we are looking at lots of these XY combinations. And one of the problems that happened in this application was there were lots of labels of gorillas, right? And it turned out that the pictures were all black, which is how it's supposed to be, because gorillas are supposed to be black, right? So a lot of label data was used to train the machine, the same way how you teach a small kid. The same example I told you a while back, right? You're teaching a kid with lots of examples of fruits. So the same way, it's almost as if you're teaching the kid with lots of examples of gorillas. You're showing it a picture of a gorilla and you're saying, hey, you know what is called a gorilla? Another picture, it's called a gorilla. Another picture is called a gorilla. Another picture is called a gorilla. Turns out there were also labels for human beings, right? Now, who is a human being? What were the kind of photos that were shown as a human? Okay, you're showing pictures of humans. You're saying, hey, this is a human, this is a human, this is a human, this is a human. That's how the machine is learning. The problem was whenever you showed pictures of humans, they were almost always white, because that is how things were in the early days of machine learning. There was a lot of biased systems that we had because the data around us were also biased. I mean, even today, if you search for the term human in Google, you'll find actually a lot of the search results, maybe 80% of your search results that are returned are white people. So even when you're teaching the small kid, the kid is picking up the color parameter. The kid is somehow mistakenly picking up that, okay, whenever I see something black, it's a gorilla. And whenever I see something white, it's actually a human. So the kid is mistakenly picking up that pattern. And that is what is going on in the model training. Okay, XY patterns, use an algorithm, build a model. So the model is built. So this is what Google Photos would have done behind the scenes. They have built a model. This would have taken a long time, a lot of processing and all that it would have taken to do that, right? Because these are like millions and millions of pictures they would have labeled to get this model. And now when you upload a photo, when you go to, you click a photo with your smartphone and you upload to Google Photos, what it's doing is it's simply doing prediction, right? So So you have the existing data and you build a model, you train a model. This is the trained model that Google Photos is having right now. And next time, you are in the Photos application now, right? So now you have a trained model. So whatever model you train, this is the trained model that you have. This is nothing but the XY relationship, the rules, right? And now next time I give you a new photo, next time I upload a new photo on Google, the model will simply do model.predict. Okay, we will simply do model.predict, and we will try to predict that based on what rules I have learned, what is the predicted value of y predicted. So this is what is actually going on behind the scenes in Google Photos and a lot of other applications. So initially some data was used to train a model, and then later on, given some new data, you are constantly trying to make a prediction. What is the result? Is it this? Is it that? So that is what is going on behind the scenes. And I know this is the gorillas example I took, but I hope you can relate to it. And this example was again to kind of really kind of help you understand that what is actually going on behind the scenes, and why some of these systems can often make very sensitive mistakes. But not quite. I mean, it does a pretty decent job. I was talking about elephants, and if I go to my Google Photos and show you pictures of elephants, it does a nice job. It does a nice job to show elephants correctly. You can see my Google Photos right now, and you can see that there are some wonderful pictures of elephants we are able to see. Okay, this is not rule based, mind you. It is not as if Google has defined a series of hard-coded rules saying, okay, you know what, pictures like this are elephants and pictures like this are not elephants. No, it is not a set of rules, but this is also learned using machine learning. Okay, so and another one fascinating, mountains, right? Mountains are very hard to, very difficult to kind of predict, and it's very hard to write rules explicitly for mountains. And if you see, even for mountains, we will actually see some excellent examples coming up for mountains. So you can go and this is my Google Photos once again. You can see. So these are examples of mountains, and it's very hard to write rules and very difficult. For example, look at this picture. I took this picture from the flight, right? I mean, I don't know. It's very hard to spot mountains, but actually there are mountains. I know for a fact there's some mountains. There's some mountain ranges you can see at the backdrop, but I mean, it doesn't look like a typical mountain. I mean, this is very clearly it's a mountain. This is very clearly it's a mountain, but look at this one. It's very hard to define rules for mountains, right? Very difficult. Like mountains can be like this typical triangular shape, or mountains may not be triangular. It is not guaranteed. Or mountains can be like this, or mountains can just be like this. No, so there's a very clear triangle that is forming, but here there is no triangle that is forming. This was a flight I took when I was going to Ladakh actually, just some time back, and you can see again it's very difficult to write rules around mountains. Very hard. Okay, and these are some fascinating examples that that machine learning can help you solve, which you cannot solve using static rules. Okay, so I hope part of this conversation everybody in the audience is able to relate how powerful machine learning can be. But oftentimes you will still see some one-off mistakes will continue to happen. Even in my photos, there are one-off mistakes that will continue to happen. A very common one will be, let's say, snow versus cloud. Very common one. I mean, if you search for snow, there might be some instances where clouds are coming, because clouds and snow are look the same. I mean, especially if you're in a flight and if you're looking at taking a picture of a cloud from flight, it looks very much like snowfall. No, I mean, if you go to a mountain range and you click a picture, it's very similar. So oftentimes those kinds of mistakes will happen, but the idea is to make the models better. And this is again a cornerstone of machine learning. You start by building a base model. You start by taking some input output data and training the model, and the most important part in machine learning is to continue to retrain the model. So initially you build a baseline model, a basic model you build, and next what you do is you try to make it better. You retrain the model, make it better. Take the fresh data, retrain the model, make it better. Take fresh data, retrain the model, make it better. So how do you continue taking more and more data, and how do you continue making the models better and better and better? So that's the whole idea of what we do uh, in machine learning. Okay, now what we will do is we'll go to the next part of our conversation, just another few more minutes of theory that we have, and just to clarify some of the jargons, because this is what you will hear a lot, right? So apart from the initial the hands-on parts that we will see, I feel it's also very important as machine learning engineers and developers to have a very good understanding of the problem statement, because you cannot just start opening up a notebook and start solving. You cannot just start coding. Okay, because honestly coding has become a very commoditized skill today, right? I mean, anybody can code today with all these generative AI tools that we have today, and a lot of it will be using in the class also. But what is very important is to have a very solid grounding of concepts, which is what we are trying to do in the initial part. There are a couple of terminologies that we are left out with, which we'll cover. So first, when we talked about, just to summarize, we started with AI, rule-based intelligence. Then we looked at something called machine learning-based AI, where machines are learning the rules. You're not hard coding the rules, but the machine is learning the rules for us. And uh, and we talked about how machine learning is done generally. Okay. Now there is one more typical term that you will hear called deep learning. Now, what is this? What is this entity called deep learning? So deep learning is typically think of it like a more specialized form of machine learning, right? So what is deep learning? Deep learning is usually a more specialized form of machine learning. So that is what deep learning actually is. So what is deep learning? It's a more specialized form of machine learning. So here also the ideas remain the same. You still take data, you still use some algorithm, and you still build a model. The machine learns the rules, the machine learns the patterns from the historical data. But the only thing in deep learning is that in deep learning, the algorithms are different, the patterns are more complex, and it is usually more favored for unstructured data. Usually when we go to pictures, images, unstructured data, text, videos, we use deep learning, which is a big part of what we'll see later on. But just remember that generally from a concept perspective, until the things that we have covered until now, machine learning and deep learning are kind of the same thing. So oftentimes we refer to deep learning as advanced machine learning. So machine learning is where the machine is learning the rules, right? So deep learning is also the same. There also we have a machine that is learning the rules, but it's an advanced form of machine learning. But the ideas, the core ideas remain, very, very similar even for deep learning. So what I want to do at this part of this juncture is to share with you another very beautiful formal definition of machine learning. And this is what was proposed by a person named Arthur Samuel. He was one of the pioneers in the field, and this is how Arthur Samuel described machine learning. It's a beautiful definition, and he said machine learning is a field of study that gives computers the ability to learn without being explicitly programmed. Right? Something we've been discussing over the last half an hour now. What exactly is rule-based intelligence, machine learning-based intelligence? I think based on that entire conversation, I think you can relate to this sentence a lot better right now. You can relate to this slide a lot better. This is a very, very important slide, I feel, because whenever you're starting with any real world problem, it is very important for you to define what type of problem it is and how you will solve it, right? Because once you have decided the approach, once you have narrowed down on the approach, the tools are the easiest part today. You've got a lot of ways how you can code and you can, get solutions to problems, right? But I think the initial part is very important, where you look at a problem statement and you try to define that, hey, is this something I can do using classical programming? Can I write a script? Can I write a rule? Can I study the system and hard code the instructions? Can I use any programming language and write a script? Can I do that? Is it possible? If it is not possible, then we use machine learning. And that's what Arthur Samuel says. We cannot explicitly program. We cannot explicitly, write an algorithm and, decide the rules here. Okay, that's the idea of machine learning. And these are the two broad categories of machine learning that we have. We have something called supervised learning and we have something called unsupervised learning. Broadly, this is how we can classify the two different forms of machine learning. We can call it supervised learning. What is supervised learning? Supervised learning is that kind of machine learning where the outputs or labels are defined. I mean, if you relate to it, this is pretty much what we talked about until now. Until now, all the examples I took, Google Photos, the XY example, the fruits classification example that I discussed, how a kid learns from lots and lots of examples of fruits. If you see in all these examples, the output is known. You are explicitly providing the outputs. You're explicitly providing information about the why. So you're explicitly telling the machine that, okay, the why is this. This is what the output is. The output is explicitly given. So the input is this, and the output is also explicitly given. And that's the way how we understand the idea of, supervised learning. Outputs are defined. What is unsupervised learning? The outputs are not defined. But this is for a later conversation. We will come to this conversation later. What happens and how it relates to machine learning. But this is typically the clustering form of problems that we will discuss later on, where oftentimes the labels are not required. If you're doing something like a customer segmentation, so you don't need to know the labels, you just need to know the information about the customers. Imagine Amazon. So you're shopping on Amazon, and Amazon is constantly capturing data about how many orders you're placing, what is the value of orders you're placing, and all this stuff. Okay, so Amazon is constantly sharing information about your orders, how many orders you placed, what value of orders you placed, and so on and so forth. So that is the whole idea, right? So that's the idea of what we refer to as a clustering kind of problem, where the rules are not defined. But this is where the traditional supervised learning rules are defined. You know explicitly what the rules are, and I'm sorry, the labels are defined. I mean to say the outputs or labels are defined. So you know explicitly what the outputs are, because if you don't know the outputs, then you cannot learn, right? The learning happens only if you know the inputs and the outputs. So the outputs are explicitly given in supervised learning, and that's why we call it supervised. Supervised, the name also suggests that somebody is supervising the machine. The machine is not learning by itself, but somebody is supervising, somebody is guiding it. There's a supervisor who is guiding the machine to learn, just like how a teacher guides a small kid to learn. You're guiding it, you're teaching it. Okay, these are apples and these are guavas, right? And there are two specific forms of supervised learning. One is called regression and one is called classification. Okay, so this is the whole stack. This is the whole stack. So supervised outputs are labels, outputs are defined, and there are two forms of it. One is regression and one is classification. So regression is that kind of problem where you're trying to predict a numerical output. Okay, so this is a numerical output that we are trying to predict. So examples could be, you are trying to predict the sales of a company. Okay, so say typical sales prediction, weather forecasting. Okay, so if you're looking at some games or some, let's say the game of cricket, okay, you're trying to predict how many runs will be scored, how many sixes will be hit. So that's typically a regression problem, because the output that you're trying to predict is a number. But there could also be some examples of classification problems. So what could be some examples of classification problems? Well, where the output is not a number, it's a categorical output that you're trying to predict. Okay, so it could be something like you're predicting that, okay, based on the features of a person, you are trying to predict, will the person have a disease or not? Yes, no. You're trying to make a numerical prediction. So will the person have a disease or will the person not have a disease? So that is how we refer to a classification problem. Or you can look at a typical network intrusion detection, a big part of what we do for the networking devices. Okay, so you have got lots of networking devices, and there are algorithms that are built in where different parameters of the network are monitored, and based on the different parameters of the network, the models are trying to classify that, is it a threat, is it not a threat. So the output is going to be something like something like a category, or something like a yes no kind of a prediction. So that's the way how we can understand the classification problem. Just to relate to this a little better, just to relate to this particular idea a little better, what exactly and maybe think of this in a bit of a better way. How can we think of regression and classification in a bit of a better way? Let's see that in action. So we have, I was taking the example of, let's say, sales forecasting, or let's say network intrusion detection. So along the X, we have, this is the input, right? So this is the input and this is the output. So what we have here are lots of features, right? So the output will be either yes or no. And these are the features, right? So X1, X2, X3. These are all the different network parameters at a particular given point in time. There are, let's say, hundreds of parameters. So these are like individual features, X1, X2, X3, X4, X5, so on and so forth. So these are all the features we have. And inputs are often called features. Like you'll oftentimes hear me use these terms interchangeably. I'll call them inputs or features, right? So oftentimes they're called inputs or features, and outputs are often called labels. There are other different terms that get used often. So inputs are called features, attributes. Outputs are called labels, dependent variables, dependent variables, and all that. But usually these are the two most common terms that are used. You call them inputs or X's, or outputs or Y's, or features and labels. So these are the different terminologies that get used. And what we again do as part of machine learning is, let's say if I want to build a kind of a intrusion detection model, I will collect a lot of historical data, right? I will collect a lot of historical data from my networking devices, and I will see based in of the last 2 years. Okay, in the pattern that is observed over the last 2 years, we are observing what happened. Okay, so whenever the network parameters were like this, intrusion threat was yes. And whenever the network parameters were like this, the threat is no. Okay, whenever the network parameters were like this, the threat is yes. And whenever the network parameters were like this, the threat is yes. So somebody will be labeling the data. Somebody will look at the historical data and they will study the network configurations at that point in time. And based on that, they will say that, okay, when the network parameters were like this, that was classified as a threat. Our security team flagged it as a risk. But whenever the patterns were like this, the security team did nothing. You will have this kind of a data. This is like the XY combination. And with this, you will train a model. You will learn the pattern. You will design the rules and you will have a working model. And next time you deploy that model, now you deploy that model, this model will run in production, live, real time monitoring the organization's network intrusion detection things, right? uh, and next time there is a new, every second or every real time it is monitoring the network parameters, and next time it gets a new set of network parameters. This is like the X new. It will simply feed that to the model. Model.predict will happen and you will get the predicted Y. So this is the way how you can think of machine learning. Use the historical data, learn the patterns, learn the association between the inputs and the outputs, and next time you get a new input, you use that to predict what is the corresponding output going to be. That's the way to look at it. And obviously, the more data you have, the more variety of data you have, the better the quality of your model. So this is how you can relate to a variety of use cases. Now you can even think of it in the context of a different kind of problem. Let's say a health data set. This was classification, by the way, because the output was categorical. It was not a number, right? You can also think from a regression point of view. Now, what could be a regression kind of a use case? Let's say from a finance perspective, a very good use case will be loan interest prediction, something like that. Okay, you're looking at a fintech company, and the company will look at the different parameters of the applicant based on your loan history, your credit score, how frequently you're able to repay your loans. We look at your different parameters, and based on that, we will predict what is your overall interest, what is the interest we will charge you, because usually risky borrowers are charged higher interest, and less risky borrowers, good premium borrowers, are charged lower interest because they have a, they are more likely to repay the loans, right? So if you think about it, again, the data would be somewhat like this. You will have some inputs, you will have some outputs, right? The only difference is the output will be a number. You will have a lot of historical data that, okay, borrowers like this were charged this much interest. Borrowers like this were charged this much interest. Borrowers like this were charged this much interest. You will have a lot of historical data. And based on that, you will build a model. And next time there is a new applicant, you will do a model dot predict and predict what the interest rate for that new applicant will be. So that's the way how we can think of what's going on behind the scenes and how we actually frame a machine learning problem. Okay, and if you think about it, these are things that you cannot do using rules, especially for something as complex as loan prediction or health classification. You're looking at the different attributes of a person and trying to predict whether that person has some disease or not. It's a very difficult problem. You cannot just identify a set of rules and say that, if your blood pressure is this, if your this is this, then you're diabetic, else you're not. It's very hard to do that because oftentimes these patterns keep changing, and oftentimes the dynamics between the features are so much that you cannot represent them using simple rules. So what I'm getting at is, in many of these real world scenarios, the rules are very hard. They're very hard for a human being to define, and which is why we resort to machine learning. We want a machine to instead design the rules for us. We want a machine to learn that particular input output relationship for us. Okay, so I hope everyone's getting a sense of it. What exactly is supervised learning, and this is the idea behind what is supervised learning. You can see the different categories of supervised learning we just now discussed. Okay, and unsupervised will come at a later time, and then there are different algorithms, and we'll see. We'll take a look at all these different algorithms as we go along. Okay, we won't see too much of theory. I think the theory part, initial phase, we wanted to clarify. We wanted to give you a solid grounding with respect to what is ML, what are the different pieces in the stack. I hope we have that solid grounding now. And from here onwards, we will straight away jump into practicals, hands-on, and we'll start building these kinds of models. Initial phase, we will focus purely on this, and then later we'll focus on this part. We'll see how this part is done. But first, our focus will be primarily on this because much of the machine learning is happening here. You'll collect your data, you'll solve regression problems, you'll solve classification problems using different types of algorithms. We'll be starting off with supervised learning a lot more in detail right now, and specifically we will talk about something called regression. And if you remember from the conversation we had in the initial part of our session, we ended the discussion here. We say there are two types of machine learning. So there is something called supervised learning. So supervised learning is that kind of machine learning where the outputs or labels are defined. We explicitly are defining what the whys are. So whenever we are building any system, we are explicitly defining what the output whys are. That is what we call supervised learning. And the other kind of machine learning is unsupervised learning, where we are not specifying explicitly what the output whys are. The output is not defined explicitly. And supervised learning can be further categorized into two parts. So we can call it regression, we can call it classification. So this is the further way we can divide supervised learning. So if we are trying to predict a numerical output, we call it a regression problem. And if we are trying to predict a categorical output, then we call it a classification problem. And we discussed about enough use cases on that. Now what we'll do is we'll get a little deeper and try to understand at a conceptual level what is regression. So before we start the hands-on, let us understand what is regression. And for this, we will start our conversation with the understanding of the straight line equation. Now, this is something that goes back to our school days. We discussed about coordinate geometry. So if you all remember, the equation of a straight line goes as y equal to mx plus c. This is how we define the equation of a straight line, y equal to mx plus c. And you can see the screen. This is your x-axis, this is your y-axis, and this is the equation of the straight line. So what are the different components of this straight line equation? When we look at the equation of the straight line, what are the different components we have here? So we have something called m. M is the slope of the line, and c is the y-intercept of the line. These are the two components of the straight line equation. So this is the equation mx plus c, and there are two components. One is the slope of the straight line. Slope is giving us an idea about, like, how much of slope, how much of elevation. Okay, so for every axis, imagine you're climbing up a hill and you look at the slope of a hill. So that is how we visualize the meaning of slope. And mathematically, when we look at a straight line equation, this is how we can think of slope. Okay, so you can see we are traveling from point A to point B. So this is the straight line. So I'm just trying to put some arrows to make it easy to understand. This is the straight line equation. And you're traveling from point A to point B. And as you travel from point A to point B, there are two types of movements that are happening. One is a horizontal movement, and two is a vertical movement, isn't it? So when you climb up a hill, you're traveling in two broad directions. So one, you're traveling horizontally, and two, you're traveling up vertically. And slope is kind of capturing both those variations of movement. So it is giving you delta y by delta x. So change of y. So y final minus y initial divided by the change of x. X final minus x initial. So we look at the change of y and we divide that by the change of x. That's how we find out the meaning of slope. So for every unit distance you travel along the x-axis, how much distance are you rising along the y-axis? So that's how we understand the meaning of slope. So for every unit distance that you're traveling along the x-axis, so x-axis is the horizontal direction that we are traveling, right? So for every unit distance that we are traveling, for every unit distance that we are traveling along the x-axis, how much distance are we traveling along the y-axis? Okay, so if this is a unit distance that we are traveling along the x-axis, how much distance are we traveling along the y-axis? So that's the way how we understand the meaning of slope. And similarly, there is something called a y-intercept. So what is the y-intercept? Y-intercept tells us that this is the point at which the line intersects the y-axis. This is the y-axis, the point in the line intersects the y-axis at this point. So this distance is called the y-intercept. So y-intercept is basically the distance of this point from the origin. It is the point at which the line intersects the y-axis. That is the y, and the distance from the origin is what we call the y-intercept. Now, this equation understanding is important because going forward, we will see that as we get into applications, we will eventually use this equation going forward. Okay. These are a few examples. You can see when the equation is y equal to 2x plus 3, this is how the straight line looks like. So 2 is the slope and 3 is the intercept. And if we have the straight line equation, which is minus 9x plus 7, then the slope is minus 9 and the intercept is plus 7. This is the way, again, how we understand the intuition behind what is the meaning of a slope. Okay, hope everybody is clear, everybody is aligned, and everybody in the audience understands the meaning of a straight line equation. Now, moving on, uh, let us try to correlate this with respect to what we have done so far with respect to supervised learning. Okay, so this is the core of what we discussed in supervised learning. If you all remember, we give the machine lots and lots of input-output combinations, 1, 2, 4, 5, 6, 7. Okay, so let me do one thing. Instead of starting this way, let me start with the whiteboard and let me explain this in the whiteboard. Okay. This is just to explain to all of you the core idea behind what is going on in uh, regression. Let us see. So we have x equal to 1. I'll take lots and lots of these XY combinations. That's the core idea. So we have XY combinations. You can see, all of you can see the screen. X is 1, Y is 2, X is 3, Y is 4, X is 5, Y is 6, and so on and so forth. So these are the input output combinations that we are taking. And now we can visualize this also in a nice way. So whatever I've written here, we can nicely visualize the whole thing. So on the right hand side, I'll draw the regression plot. This is how the regression plot will look like. So we have x-axis, we have y-axis. I'm sorry, this is the y-axis. So this is x-axis, this is y-axis, and these are our data points. This is 1, 2, this is 3, 4, and this is 5, 6. Okay, so this is pretty much the idea of what we have discussed in supervised learning so far, isn't it? So we are looking at lots and lots of these input-output combinations, or so-called XY combinations, and on the basis of these input-output combinations, we are trying to find a line or plane or mathematical surface that best fits the points. So in a way, we are trying to find out the line of best fit. So what is the best fit line? We are trying to kind of find out the best fit line. So the best fit is what we are in a way trying to find out. So what is that best fit line? How do we do that? How do we visualize the best fit line? So this is the way how we do this. Okay, so I'll take a scale and try to explain. So this is my 1, 2, this is my 3, 4, this is my 5, 6. So what is the algorithm actually trying to do? What exactly is the algorithm trying to do? This is pretty much what we discussed in the morning part, right? So we talked about the data. This is my data, and we are using some algorithm, and we are building a model, right? So the model part is the end result of what we are getting. So what is this entity doing? How are we learning? What is this fit happening? What is this model dot fit? What is this fit? What is this model training? How is it training? How is it learning the rules? So given this data, we are trying to find out what is the line that best fits the points, right? I know this doesn't look perfect. Let me just try to realign the points a little. Yeah, don't worry. I mean, this is 1 comma 2 will be somewhere here actually, little raised. 3 comma 4 will be little raised. Otherwise, actually, my line was passing to the origin, which is not right. Anyway, so now we are trying to find out, there are infinite number of lines we can draw, right? If you look at this 2D, two-dimensional mathematical surface. So in this two-dimensional mathematical surface, there are infinite number of lines we can draw. And out of all these infinite number of lines, we are trying to find out what is that line that best fits the points. That is what we call the regression line. So out of all the infinite number of lines that we can potentially draw in this two-dimensional mathematical space, out of all the infinite number of lines we can draw in the two-dimensional mathematical space, we have the line of best fit. That is what we call the regression line. And you want to know what is the equation of that line? The equation of this line, interestingly, so this is the best fit. The best fit we have got, right, is y equal to x plus 1. Okay, and I think this is based on everything that we saw until now. See, the slope is 1. This is, if you compare this with the template that we talked about, mx plus c. See, the m is 1 and the c is also 1. So the slope is 1 and the intercept is also equal to 1. So that's the overall idea. Okay, so this is the best fit line that we have got. And this is how it relates back to everything that we talked about so far. So we have the data. We are using the regression algorithm. There is some algorithm that is playing out behind the scenes. There's some best fit line that we are trying to draw. And what is the model? What is the rules? Or what is the mathematical function that we learn at the end of it all? It is y equal to x plus 1. So we can see it visually and we can also see it mathematically. See, even mathematically, if we try to do this manually, the relationship between x and y is y equal to x plus 1. This is what happens in model training. So when we talk about training a machine learning model, this is effectively what we are doing. We take the data, we try to find out the best fit, we get the equation, and given some new x, given we have some new value of x, we can fit this into the equation. I mean, if I have to do this visually, given I have a new value of x, what I will do, let me erase this part. So given I have a new value of x, let's say x is equal to 9. One, I can substitute this to the equation, and this time I will do a model.predict, and y is equal to 10. Predicted value of y is 10. Visually, how will I do it? Next time x is equal to 9, you try to extend, and you predict, hey, given this is the line, if x is 9, the predicted value of y will be equal to 10. So that's the way how you can visualize what is going on in linear regression. I know there are a lot of questions that people will still have. One very common question that you will have is that is it guaranteed that the line will perfectly pass through all the points? No, it's not guaranteed. I mean, the line is not, it's not guaranteed that the line will perfectly pass through all the points. It's possible that the line, that we are talking about will not pass through all the points. Okay, so that is one thing that everybody will need to keep in mind. Okay, so it is not absolutely guaranteed that whatever best fit line that we have right now, it is not guaranteed that the best fit line will pass through all the points. It is called best fit, but it may not be a perfect fit. So what I mean to say is you can still end up with a scenario like this. You might have a set of data points that are a little bit more distributed a little bit more naturally, and then your best fit line will be somewhat like this. It's a best fit. It's not a perfect fit. It won't pass through all the points, but it is going to pass through most of the points. So that's one of the variations that I want to talk about. The other variation is that the equation need not necessarily be linear. Okay, so whatever equation that we learned here, it doesn't necessarily have to be a linear equation. You can also end up learning a non-linear equation. So we have some data, we use some algorithm, and we can also end up with a non-linear model. Okay, so instead of a line, this is a linear model. We can end up with a non-linear model that passes through all the points. So that's the other aspect that I want to also talk about. Okay, so this is all. This is what initial part is about. So we talked about what is a straight line equation. We talked about how to visualize this and how to correlate this idea with everything that we talked about so far. So this is what we discussed, how we find the best fit line, and this is the way we visualize regression. Whatever we'll do in code now over the course of the next 1 hour, this is the way to visualize what is exactly is. This is the best fit case, but it need not be best fit. And the second idea is that it doesn't have to be a single variable. What I explained right now was with respect to a single input or a single feature. Okay, so it is like, let's say we are trying to predict the salary of a person. A very good use case of regression is in the HR department. Let's say you have a new applicant, you have a new uh, employee that you want to hire. The person has gone through on the rounds, interview rounds, and they have cleared the interview. And you're going to be offering the person a role in the company. And a good use case would be to predict the salary. This is a very good use case of regression. So how will you do it? What's the idea behind it? So you will look at the historical data in your organization. So it will be somewhat like this. You have the experience, which is the input, and you have salary, which is the output. Okay, so you look at the historical data. You look at how people in the company, how much money they typically make. Okay, so you look at the historical data in the company, how much money people in the company typically make. So when somebody's experience is this, their salary is this. When somebody's experience is this, their salary is this. And when somebody's experience is this, their salary is this. So we are looking at the historical data in the organization. We are looking at the patterns. What is the experience? What is the salary? What is the experience? What is the salary? And again, what is the experience? What is the salary? We're looking at the historical data. And based on the historical data, we will use some algorithm and we will build a mathematical model. We will find some relationship between the X and the Y. So this is in line with what happens in the company. In the company, you're trying to figure out that, hey, what is the typical pattern? What kind of money do people typically make based on their experience? And you learn the relationship. You learn the some equation between X and Y. Let's say this is the equation that you learn. It's very generic, I know, but let's take an example. So this is the model that you learn based on your data. Now what will happen? Now let's say you will use this model for your future hirings. Okay, so that's machine learning, right? So you take the data, build a model, dot fit model training, you train the model, you learn the rules. And next time a new applicant is to be offered, if the experience of the person is 5 years, so this person has 5 years of work experience, and based on that, you will predict what is the salary. So now what will you do? There are two parts. One is model.fit, and here it will be model.predict. Because you already learned the equation, you have the rules, and now that the experience is 5 years, you put 5 here. 5 into 2 is 10 plus 1, 11. So the model will predict 11 salary. So that's the way how the two components are working, fit and predict. Now, very important. Here, I used only the experience to predict the salary. I mean, we are framing it as a very basic problem. We are looking at the experience of the person, and based on the experience of the person, we are trying to predict the salary of the person. Very basic use case. Okay, we are looking at the experience of the person, and based on the experience of the person, we are trying to predict what is the salary of the person. That's the way how we are framing the whole thing right now. But if you look at a real world scenario, the salary of a person actually depends on many other parameters. The salary does not just depend on the experience. The salary of a person depends on multiple other parameters. The salary will depend on your experience. The salary will depend on your, let's say, the interview rounds, how much of marks you scored. Your salary will also depend on your skill set. So maybe if you're applying for an AI team, your salaries scale will be very different. If you're applying for a full stack development team, your salary scale will be very different. So the salary of a person, the output will depend on many other inputs. Even during the model training, while you're framing the problem, this is a very, very important part of ML, where you have to decide, you as a developer, you as a data scientist, you will have to decide that when you want to predict the salary, what are the inputs which you can use to predict the output? What inputs will have the highest relationship with the output? And that is where we will typically do relationship with regression with multiple variables. So the example I showed you here was with a, based on single X, you're trying to predict single Y. It's easy to visualize, but oftentimes we will end up with more complex use cases like this. So the same way that we can have a straight line equation, we can also have a planar equation. So y is a mathematical function of multiple features. You can see m1x1 plus m2x2 plus c. Similarly, you can extend it. m1x1 plus m2x2 plus M3x3 plus 3 plus C, or M1x1 plus M2x2 plus M3x3 plus M4x4 plus C. You can have the output Y, which depends on multiple input X's. So the output depends on multiple input features. That is the idea. And this is what we refer to as multiple linear regression. Okay, and you can see the ideas are very, very similar. The only thing is that instead of a line, so now what we have instead is basically a plane. So that is the only difference that we have here. Instead of a line, we now have a planar equation. Okay. Now let's move on. Let's come back, and this is just one more way to relate to it. This is a little bit more technical in terms of geometric understanding. So if you remember, we talked about slope a while back, and I discussed that slope tells you that for every unit increase in x, what is the change in y. So this is the way you can understand what slope means. What is the meaning of a slope? So for every 1 unit increase in the value of x, what is the change in the value of y? So for every 1 unit increase in the value of x, what is the change in the value of y? That is how we define the meaning of slope. Now, if you relate it to the examples that we did so far, let me take you to this example. Y equal to, excuse me, y equal to 2x plus 3. If you look at this example, imagine this is the example we did with respect to salary and experience. I'll call it salary. So y is the salary and x is the experience, E. What it means is for every 1 unit increase in experience, the salary goes up by 2 units. So this equation that you're seeing on the screen, whatever this final equation that we are learning, so we take the data, use an algorithm, build a model, which is an equation form. That final equation that you end up getting, there is a lot of meaning hidden into that equation. You can really understand in detail what that equation means. So in this case, y is equal to 2x plus 3 means that the slope is 2. And what is the meaning of this 2? What do we mean by this slope 2? Slope 2 means that for every 1 unit increase in experience, the salary goes up by 2 units. So when we look at the entire historical data of all the employees in the company over the last 5-10 years, this is the pattern that we have discovered. When we do that best fit line, this is the general pattern that we have discovered that usually on an average, see, there will always be outliers, there will always be exceptions, and some people are making a lot of money, some people are maybe, let's say, this whatever reason they've taken from a different sector, domains, career breaks, and maybe they're not on the same pay scale, or their progressions and promotions are due. But if you look at the general average trend in the company, on an average, for every 1 year increase in experience, if you see the line, for every 1 unit that you travel forward, on an average, whichever part of the line you see, from here, whichever part of the line you see, for every 1 unit that you travel ahead, you'll go up 2 units up. That's the idea. Okay, and the same way, what we can do, the same way you can also see a similar pattern with respect to multiple linear regression. This is the thing I wanted to highlight. So this is the equation of a line. Similarly, this is the equation of a plane. There are two variables, right, to predict the output y. And this is the example. Remember, salary equal to experience plus marks plus C. And this is the way to interpret this. Okay, this is the way you interpret the meaning of multiple linear regression. If there are multiple inputs which are used to predict the salary, once you get that equation, you get a very nice interpretation of what that equation means. And that is, I would say, one of the most powerful features of linear regression. It is a very basic algorithm. As we go through the topics, we will discuss more advanced algorithms which may not take the shape of a mathematical equation as simple equation that we are seeing here. But even this very, very simple equation has extremely powerful qualities because it helps us understand what is going on behind the scenes. The interpretability and the explainability is very high. So by looking at this equation, we can say that on an average in the company, keeping other factors constant, if the experience goes up by 1 unit, the salary goes up by 2 units. And keeping every other factor constant, if the experience goes up, if the marks goes up by 1 unit, the salary goes up by 3 units. So this is very interesting, which tells you that the marks has a very, very important role to play on the salary. Even if you get more, let's say it's a very scientifically developed exam. Let's say company all the company employees have come together, all the departments have come together and framed the questions as an example. So they have tried to frame the questions in line with the kind of work they do, the use cases they follow, and all that. So they have designed a very exhaustive set of questions, and they have discovered that over the years, that every 1 unit increase in marks, if some of the candidates are scoring even 1 mark more, that translates to a to a 3 lakhs increase in salary. And I'm just saying as an example because 1 marks is scaled data. And don't think it's on a scale of 100. So maybe let's say out of a scale of 10, it's scaled data that we're taking. Okay, so on a scale of 10, let's say every 1 mark more that you score, the difficulty level as it gets harder and harder, your pay scale on an average goes up. Okay, keeping other factors constant. Now keeping these ideas in mind, what we will do is we'll go to our first case study, which is an advertising data set. So the data set is actually quite simple, and this is also an example of a multiple linear regression data set. Now that we have all the theoretical grounding with us, and this is what I meant to say, that we'll strike a balance. We'll not get too deep into the theory and the algorithms in detail, but at the same time, we will not completely skip it so that you know to some extent what is going on. Now, from here onwards till the end of the day, as we go through the demos, we will not get back to the theory again. We will not get into, okay, hey, what's going on? What is the algorithm and all that? So now we will purely focus on the practical. We'll purely see how things actually are done in the notebook with some basic references to theory as and when required. Okay, but the grounding is set. That is the most important part. So this is the data set. We have the TV, we have the radio, we have the newspaper. So we are looking at the use case of a company, and the company is spending a certain amount of money in TV. This is TV advertising expenses. We're looking at advertising money. How much of money is the company spending on the TV advertising? How much of money is the company spending on the radio advertising? And how much of money is the company spending on the newspaper advertising? So based on the amount of money the company is spending on all these advertising avenues, so based on this amount of money that the company is spending on all these advertising avenues, we are trying to predict, okay, based on this amount of money the company is spending on the advertising avenues, we are trying to predict the sales. It is a sales prediction that we are trying to do. Okay, so purely based on the advertising expenses, we are trying to estimate the sales. We are trying to predict the sales. How much sales are we going to get out of it? So that is effectively what we are trying to do. It's a sales prediction that we are trying to do here, sales forecasting. So it makes it a regression problem because you can see these are the input x's. If you have to frame it in line with what we have discussed. So this is more like a the input x's, input x1, input x2, input x3. And based on all these input x's, we are trying to predict the output y. Okay, so this is what makes it a kind of a regression problem. So now let us see the solutioning. Let us see how we can solve it. And this is the first time we are actually seeing something called a Jupyter notebook. This is the setup we already did. So this is my Jupyter notebook. I'll double click on it and I'll open it on Collab. So all of you can first follow on what I'm explaining, and then I will give you some time to run the code. Okay, and so first just follow on what I'm explaining. Just another 5 to 10 minutes we will take to explain some parts of the demo, and then we will take some time to give you some time to run the code and do some more case studies on that. Okay, so this is the plan. All right, so now first things first, this is my data. So, and whatever you see right now, this is called a Jupyter notebook. Okay, so you can see the extension of the file is IPYNB. IPYNB stands for Interactive Python Notebook. It's a notebook file. It's not just a Python script. The language that we are using is Python. The inherent language that is used is Python, but it's not just Python. It is Python and something else. So whatever we are seeing on the screen right now is not just Python. It is Python and something else. And what is that something else? What is that something else that we are talking about here? So that something else is relating to. So that something else is relating to the markdown syntax. It's almost like HTML. Some of you who can relate to front-end development, HTML is a markup language. And if you see a markup language, what we do in a markup language is we decide the structure of the web page. Okay, we decide the contents of the web page. What is the text, what is the body, what is the paragraph. Some of you would have done this long back, like we use HTML tags, paragraph tag, heading tag. We decide the entire structure and layout of the web page. So something very similar here also. So we use not only the Python language. You can see this is a cell. These are called cells in a Jupyter notebook where the Python code is demonstrated. And obviously, it's an interpreted language. There's no compilation. So every time we have a cell, in a cell we have multiple lines of Python code. And if I hit run, all these code is getting executed, interpreted. So we run the code, we get the answer. We run this cell, we get the answer. So it's an interpreted language. But the best part is it's not just the code. We also have the markdown. Okay, so we can actually create a text cell, a markdown cell, multiple different types. You can actually create a kind of a text cell where you can write markdown syntax. And this you can use for giving headings. You can give titles. You can, all of it you get to see in one interface. And that's why the term Jupyter notebooks. Okay, you can of course, convert this back to a py file. If that is something you're more familiar with, you can convert it to a Python script. But what we are seeing is notebooks. Now, what is the reason why we don't directly use a Python script? Why do we do development? Like if you look at data scientists and the developers, why we prefer doing development in this kind of an interface? Okay, the reason is simple, because while you're building models, while you're building machine learning models, there is a lot of explorative work that happens, a lot of exploratory work that happens. Okay, so because oftentimes what we will do is we will look at the data. We will spend a lot of time in the initial phase where we look at the data. We try to figure out what are the missing values. We try to figure out what are the outliers. We try to figure out if we need to add some columns, remove some columns, create some calculated columns. So we have to do a lot of that work. And also there are times when we need to plot something. We need to see some patterns. We need to see some correlations. All those things we will have to do. And then we will explore, even during the model building phase. Remember, I told you that we have data and we will use different algorithms and we'll try to build different models. So we'll do that. We'll try to build different models and we'll see the best one. So all this is something that we need to explore. It is not like how we do traditional programming where we have a set of steps and we know the requirements of the system, and so we start coding, we write our conditional statements, our loops, declare our variables, and we go on. No. But what we want to do here is, this is not like a single set of instructions we are writing. It's a very exploratory way we are doing the entire development. So the process of the initial model building phase, Jupyter notebooks are standard in the industry. So right now we are using Jupyter notebooks that are hosted on Colab. It's free. We are getting a free virtual machine. But you even have Jupyter notebooks on Azure. You have Azure notebooks. We have Google Cloud, Jupyter notebooks on Google Cloud, and we even have Jupyter notebooks on AWS SageMaker. And I just named three of the most popular cloud platforms that we have. So if we have Azure, inside Azure Machine Learning Studio, we have notebooks available there. If you are using AWS, you have something called AWS SageMaker, and there are SageMaker notebooks available there. And similarly, you've got notebooks inside Google Cloud. Okay, so notebooks are absolutely the backbone of data science, machine learning, deep learning development. Once you have built the model, so in other words, once you have learned the rules, once you have the final equation, okay, so once you have designed the model, once you have built the model, now you can go and you can absolutely, kind of, so once the initial model building is done, now you can absolutely go and you can effectively convert it to a script and deploy. So the final deployment part is usually done through a script. After the initial model building has happened, then you can convert it to a script and that can be used for deployment. So that is the next phase that can happen. Okay. Okay. Anyways, now let's quickly take a look at this notebook and understand how what the different parts of this notebook are. Okay, what are the different parts? And as I told you, like we'll try to focus on the practicals. We'll not get too much into the underlying theory of all these things because each of these are extremely deep topics. And even if you look at a typical university program, many of these PG programs that are running, each of these are like 1 year long courses. So even in this simple notebook that you are seeing on the screen, there is a lot going on. So I've shared a lot of code, lot of steps, and it's not possible to go over every single part, neither is it needed. So if you want some help, if you want some references, do look up. Okay, but all of the steps are not necessary for building a solution. Okay, so what am I trying to say? Okay, let's look at the very first, a very simple machine learning model. And I think what I will also do is, although it's not a planned topic that we have, but I wanted to show you. This is the initial cells, and this is the way you run a cell. Okay, this is the way you can run a cell. I have also done something a little different right now. I'm actually doing something called mount.collab G drive. Now this part is optional. If you want to do it, you can. Otherwise, you can ignore it. Okay, this is basically done to make sure that uh, you are mounting your G drive in this folder space. Now that is completely optional. If you don't want to do it, please leave it. What is the benefit of doing it? What is the benefit of mounting your G drive here? What is the main benefit? The main benefit would be then you can access your G drive files. So remember, my advertising.csv file is present in this advertising case study folder, which is in my Google Drive, right? This is the folder. And if you see the entire path, this is where my folder is present. So the only difference is that, when I mount my G drive on Collab, my G drive will be visible here. But I think if this sounds too complicated for some of you, you can completely ignore the step. You can just download the files as and when I'm sharing. See, I'm downloading the file now. I'm downloading the file now. After a while, it will be downloaded. And once you have downloaded the file, you can simply upload it here. That's it. So you have downloaded it. You can simply upload it here. That's it. Just drag and drop the file. It's a two-part process. Okay, so once you have downloaded the file, you can just go and upload the file. It's just a simple two-part process we can follow. Okay, and what you can do now is uh, you can go and effectively drag and drop the advertising CSV file, and you can just put it here. So now that we have the file, we can easily read the file. You don't need to easily to modify the path right now. So you can see that this is my present working directory. I'll skip the initial part because I told you it's not needed. You can comment out this cell and you can just run the cell. You can click on the play button, or you can just hit Shift Enter as a shortcut. If you want to get some help on the shortcuts, you can find the shortcuts present here, but you can just do hit the play button otherwise. It's an easy way to run the code. And this is the actual Python part where it starts. You can see we are first loading all the Python libraries. In fact, this is what makes Python such a powerful programming language. Not just because the language is easy, not just because it's a high level language, it's easy to work with, but because of its extremely uh, very rich availability of different libraries and frameworks that support the language for different tasks, right? Python is a general purpose language. So, right now we are looking at Python from the perspective of data science and machine learning, but I'm sure a lot of you in the audience, you have used Python for other things like scripting for web development. Okay, so Python has some very good, powerful frameworks, front-end frameworks like Django, which are written in Python. Okay, so you can do a lot of stuff with Python, not just what we are learning. But obviously, the libraries and other things we will be using, the frameworks we'll be using, will be specifically for data science and machine learning. So first, we are importing something called pandas. Import pandas as PD is basically it's a library that is used for data manipulation, and it helps us to work with data frames in Python. Okay, so we will basically be using the pandas library, and we will use the pandas library to to go and do to manipulate data frames or tables in Python. Tabular data is what we are working with here. Okay, so if you have a table, if you want to add some columns, delete some columns, you can work with pandas. Okay. Then we also have something called NumPy. NumPy is basically the base mathematical library, the numerical computing library in Python. So NumPy stands for numerical Python, and we can use it for for performing different numerical operations. So we can use NumPy for that. So NumPy stands for numerical Python. Okay. Seaborn and Matplotlib are typically data visualization libraries. So we can take a data set, we can create a bar chart, pie chart. So we can create different types of visualizations using these libraries, heat maps and all that. And next thing is the warnings library, which we are using to ignore the warnings. So oftentimes these are all open source packages, right? So sometimes some version is, let's say, rendered, like is deprecated, and also some of those error messages might come up, which are pretty annoying. So you can opt to ignore all the warnings in your files. Now the next part is where we are actually loading the data. So as I told you, I'll comment out this piece of code because we'll be taking it locally. I'll just comment out this initial part of the code. And I'll just be saving the work, as and when I save anything, you'll see the same file reflected in your Google Drive, but everybody knows what to do. And all that I will do is I will just add another piece of code and say demo equal to pd.read CSV, demo equal to pd.read underscore CSV. Okay. And hey, I mean, look at this. Look at this. Isn't it incredible? What you're seeing on the screen is Gemini. This is Google's Gemini. So even before I type something, Gemini knows what I want to do. Can you see when I start typing pd dot? So it's almost like Gemini understands what I want. Can you see? Can you see the suggestion coming up? This is incredible. So we'll get used to more of this as we go along. But once you see a suggestion, just hit tab, and Gemini will autocomplete for me. There's a lot more we can do, and I'll walk you through some of the other coding features. What are the other really cool things that Gemini brings to the table inside Colab? So there's something called Gemini. Gemini is Google's uh, native large language model that is there in all the different Google products, which is including Google Colab. You have it in Google Colab, Google Drive, Google Docs, okay? Everything with plans to have it in Google Photos and everywhere, basically. And so what it does is, as you start something in Colab, as you start programming in the collaborative environment, so Gemini will read the entire file. It will read the entire file, and you can basically ask questions about your file. This is not just like a normal chatbot. This is not a normal Gemini chatbot that you open and start chatting. No, this is very, very context sensitive. You can literally ask it questions from the code that is present in your file, which is what makes it very powerful. You can see it says analyze your files with code written by Gemini. So you can literally upload a file and you can ask Gemini to summarize it. And we'll see this. As we go along, we'll see some more examples of this in action. But for now, let's come back to the basics, because if we straight away start learning Gemini, then you'll probably feel like none of what we are studying is even relevant, because honestly, nothing is relevant. After all these tools and everything that we have today, I mean, they're doing everything for us, right? So, but yeah, the fundamental concepts are still very, very important, but we'll come to those parts at the end, okay? So pd.read CSV, we load this into a demo data frame. This is the data frame in Python. And we will see dot head to see the top 5 rows of my data frame. I again did shift enter to run the code, or clicked on the play button, you can see. And whenever you generate code, see, this is the part where I hit tab. You can see that Colab will automatically put it'll put a small gray icon which says that, hey, I think you generated the code. So this is the warning sign. It's nothing wrong in that, but just wanted to let you know that in case you're doing this for some customer or doing this for some client demo, just be very careful that when you generate code with Gemini, you get a small kind of, like, you can remove it also. I mean, but yeah, I mean, you cannot, like, you can see, there's no way you can, like, you cannot delete this thing. So just be careful of that. So maybe you can copy it and paste it somewhere else. Okay, so whenever you generate code, there's a small license thing that will come up, and it'll also give you, it'll also basically give you some sources, like from where did Gemini look up the code, because it's a language model. It is also trying to look up the code and give you suggestions from somewhere. Okay, so it's actually going to give you, like, what are the sources that it is pointing to. So when it said reads.csv, advertising.csv, it kind of pointed to this particular source. Maybe there was something in this source. Maybe this person who is that finger thief, whatever, Michael something is his name. Maybe this person also did the same advertising.py dataset, linear regression.py, you can see. So maybe the person did something very similar. Okay, so this is the thing. We have loaded our data. We know the X, we know the Y's, all that we can do. So we can see the type, and you see a whole host of options will come up. You can generate plots. You can view recommended plots. There's a whole lot of things you can do with Gemini. You can see type of demo. When we see type of demo, we see a pandas data frame. This is actually a data frame. A data frame is nothing but a simple table in Python. It's another fancy way of calling it a table. It's nothing but a table in Python. And now we can drop that unnamed column. So remember, there was a first column was actually not useful. So we can drop that column. And this is the structure of my data frame. If you see the structure of my data frame, we can see there are total 4 columns we have. We have TV, we have radio, we have newspaper, we have sales. And these are the 4 columns we have. And the output column is sales. So based on the TV and radio and newspaper, we want to predict the sales. Okay, so based on these 3 columns, we want to predict what the sales will be. So that's the objective that we have right now. Okay, and then we have some other basic, exploration features we can continue doing. These are again, we can, you can see. And the most important part actually starts from here, where we segregate our data. And this is where we'll start from. We need some X, we need some Y. So all of our discussion in the initial few hours were focused on this. We need some X, we need some Y. And this is the part where we do the segregation. We say X equal to demo TV and Y equal to demo sales. So we are very clearly segregating what is my input X. X is my TV. So TV is my input. The amount of money that you're spending on TV advertising is my input X. And the sales that you're getting as a result is my output Y. So that is the thing that we have done. And now based on that, we will go and build a machine learning model. So there are some visualizations and all that I've done here. You can ignore all this. It's not so important right now. I want to take a minute to talk about the heat map though. The heat map is a very interesting thing. This actually tells you correlation between the features. Okay. So what is this diagram telling you? First of all, the code, it is data.core. Okay. And again, like one way to learn is obviously you can go and, you can kind of look at the code, and one part is I'm explaining. And if you need some help and if you want to learn something by yourself, obviously that will be a big part of your learning going forward. You can open up Gemini and you can just say explain the code. So you can just paste it here. Just paste it here and just say explain the code. Just say explain the code, and it will do a very nice job of explaining the code. Just say explain this. I think I didn't copy this, so just copy the cell, and you can go and you can effectively go and copy the contents. You can copy the contents of the cell. Okay, so I can just go and copy the contents of the cell, and once you do it, actually it's copy selection, and once you do it, you can go and paste it, and you can say explain this, and it will very beautifully explain what this thing does, what are the different components. It's a very detailed explanation. Okay, and if you just further say summarize this, it will actually give a very nice summary in terms of what these different things are. Okay, so this is kind of learning guide you can all use. So you can use these kinds of generative AI tools as a very good learning guide. Okay, so I think it couldn't understand. Anyways, let's leave it. So you can see this is what correlation does. Anyways, what is correlation? Let's try to understand this a bit more in detail. Remember, one very important idea that we covered was whenever you're trying to do machine learning to predict some output, you need to choose what input features you want to take. Right? You want to choose what are the inputs which are good predictors of the output. That part is very, very important. We have to put a lot of focus to choose which are the inputs which are good predictors of the output. Isn't it? Imagine there was a salary prediction model that we were discussing to start our, like we were talking about that model to start with. And we discussed that to predict the salary of a person, what are the most important predictors of salary? So if you want to predict the salary of a person, what are the most important predictors that are used to predict the salary? What are the most important predictors? Because if you can choose those predictors or inputs well, then you will get an accurate prediction. Okay, so it's very important to choose those inputs or predictors properly. If you can choose those inputs or predictors properly, and if you can choose inputs which are good predictors, then your outputs will be more accurate. Imagine if you are trying to do sales prediction. Here we are doing sales prediction. So these are relevant inputs, right? I mean, so the sales of a company indeed depends on their advertising expenses. So if you're spending more on a particular TV platform, for advertising money. If you're advertising more, you will get more sales. You will get more visibility amongst your prospective customers, and people will know about your products and they will buy your products. So sales will inherently go up, right? Is expected. But what doesn't make sense is if you want to predict your sales, you will not want to predict your sales based on um, the average age of your company. Doesn't make sense, right? So the age of the company has nothing to do with sales, right? I mean, we can argue that okay, if the company is older means I mean to say the like how when it was established. I mean, a company can be established 20 years back. A company can be established yesterday, but the sales is not a direct, factor of that. There are a lot of companies which were established uh, 50, 70 years back as small family businesses, and they are doing no sales at all. They've all shut down, let's say. But imagine there was a company that was established just yesterday, a very new startup company, and they are doing brilliant sales. So the sales doesn't depend too much on the family history, the establishment history, but sales is ultimately a function of how much you're able to make your consumers aware about your product. Are you advertising more? Are you having a good quality product? It depends on those fundamentals. How strong a team do you currently have? So the current indicators matter, not something you did 70 years back matters. Of course, there are established businesses which are outliers, but generally, what I'm getting at is the output. Whenever you're framing any data science problem, it is very important to identify what inputs are predictors of the output. You will not want to consider some input X, which is a bad predictor of the output Y. And that is where the correlation matrix gives you a very good understanding. And this is again a very theoretical topic. If you remember, we were looking up Gemini. Gemini did give us something called Pearson's correlation and all that. So it's a fairly theoretical topic, but the core idea is uh, correlation typically ranges from -1 to +1. If you look at Pearson's correlation coefficient, it typically ranges from -1 to +1. So this is the range of Pearson's coefficient. -1 to +1 is the range. And the most important factor is the magnitude. We look at the magnitude of the correlation. How strong is the correlation? There are two aspects. One is direction, one is magnitude. Direction will tell me, is it positive, is it negative? +1 means positive correlation, -1 means negative correlation. That is how we understand the direction of the correlation. What is the direction of the correlation? Magnitude of the correlation tells us how strong is the correlation. Is it a strong correlation? Is it a weak correlation? So what is important for us is to understand the strength of the correlation, not so much the direction. And you can clearly see that between sales and TV has a very strong correlation with sales, 0.78. Actually, TV has the highest correlation with sales, which means that if I know that I'm spending more on TV, definitely I will get more sales. So you can use this as an indicator to understand which are good quality features. Even similarly, the next best feature is radio, and the next best feature is newspaper. Newspaper is actually a very poor quality feature because correlation 0 means it's a very bad correlation. Positive is positive correlation. One is more, the other X is more, Y is more. Negative is negative correlation. If X is more, Y is less. And 0 is 0 correlation. There's no relationship. Right? That's the idea. And if you want to get a little deeper into this topic, maybe it is justified to talk because it's a bit of an important topic also. I can take you to my notes and just give you a slightly deeper understanding of correlation. Yeah, I think this diagram will clarify everything about correlation. See, look at this one, all of you. We have two variables. We have ice cream sales and temperature, and we are studying the relationship between ice cream sales and temperature. So we are looking at day-wise data. Each and every day, we are tracking what is the temperature of the day and how much of ice cream sales we are making on that particular day. And we can clearly see when we go and plot this data, we can clearly see that more the temperature, typically more the temperature, more the ice cream sales. This is what we refer to as positive correlation. If the X is more, the Y is also more. If the temperature is increasing, the sales is also increasing. So similarly, we can look at the next one, which is temperature versus jacket sales. So as the temperature increases, the jacket sales decreases. This is what we refer to as negative correlation. This is minus VE correlation, negative, inverse. So as the days get hotter, people buy less jackets. We are seeing a kind of a downward spiral. Similarly, we are seeing two more examples. You can see income versus spending. Income versus spending is a positive correlation because typically more the income, more the spending on an average. There can be some outliers. There are people who are earning more, but they are spending even lesser. Maybe at a point in time in life when you tend to earn more, you also tend to save much more. So your corresponding income actually reduces a lot more. That is also possible. So, and another very interesting thing that is happening here is another very interesting thing that is happening here is if you see, uh, if your income increases, spending increases on an average, but it's a lot more spread out. It's not the same strong relationship we saw here. The relationship is not that strong as we saw here, but it's more spread out, it's weaker. And the same applies here, health age versus health quality. You can see that as the age increases, the health quality reduces. Again, it's a weaker correlation. So as we see these examples, how are we measuring correlation coefficient? We are measuring this using something called Pearson's correlation coefficient. Now, this is the part where I was mentioning that, in bits and pieces, we will end up coming across some jargon, some theory, but don't worry, right? So these are some mathematical parts which you don't need to worry about, but understand the concept behind it. That's most important. So we use something called Pearson's correlation coefficient, which is given by small r. And the Pearson's correlation coefficient is usually ranging from -1 to +1. And there are two aspects to the Pearson's correlation coefficient. Now, these are the numbers I've generally given. Don't worry how I'm getting these numbers. These are only random numbers I've given, 0.9, 0.4, 0.3, but there are ways to calculate it. But here in this example, I've just randomly given the numbers. And whenever you look at any particular value for the Pearson's correlation coefficient, there are two aspects that should come to your mind. Aspect number one, we should look at the direction of the correlation. Is it positive? Is it negative? Aspect number two, we should look at the magnitude of the correlation. In other words, what is the strength of the correlation? Is it a strong correlation? Is it a weak correlation? So these are the two broad aspects that we have here. So first, we have the direction of the correlation. Direction could be either positive or negative. So is the direction of the correlation, is it a positive correlation? Is it a negative correlation? That is the first part. And the second is the magnitude of the correlation. How strong is it? Is it a strong correlation or is it a weak correlation? How strong is the correlation? That means if you look at the example, it is the magnitude actually. And generally, the closer the points are to each other, the stronger the correlation. If the data points are stacked very close to each other, so if whatever points we are seeing, if they are very stacked to each other, they're stacked very close to each other, it's a strong correlation. The correlation is very strong. But if the points are more spread out, if the data points are more spread out, then the correlation is weaker. So that's the way we understand the meaning of correlation, right? So if the data points are stacked very close to each other, we have a strong correlation. And if the data points are more spread out, we have a weak correlation. And now with this understanding, if you go and look at the diagram, if you look at the diagram that we have here, look at the first one. I think you will agree with me that 0.91 is a strong positive correlation. Two things. One is it is a positive direction. And second is it's a very strong relationship because you can clearly see that as x increases, y also increases. If x is more, y is also more. Okay, so as x increases, the y also increases. We are seeing a strong positive correlation. Similarly, if you look at the next example, you can see minus 0.95. We are seeing a kind of a strong negative correlation. So minus 0.95, we are seeing a strong negative correlation. So we are seeing as the x increases, the y kind of decreases. So we are seeing a strong negative correlation here. So as the x increases, the y decreases. So the correlation is negative. It's inverse, as you can see on the screen. It's inverse relationship. And it's also strong. It's strong inverse negative relationship. And if you look at the last two are great examples, which highlights the magnitude property very nicely. You can see the last two examples, which, as I said, they They highlight the magnitude property very nicely. So you can see income versus spending. This is a weak positive correlation. Why is it a weak correlation? Because you can see the data points are more spread out. It's positive. Why? Because if income is more, spending is more. So that is the direct proportion we are seeing. If one is high, the other also increases. It's also high, and it's weak relationship because as X increases, there is no clear pattern for the increase in Y. Y increase is more haphazard. So that's why we are seeing a weak relationship here. Whereas this one is also a weak negative correlation. So this is a weak positive correlation. This is a weak negative correlation. You can see as age increases, the health quality reduces. So more the age, lower the health quality. So yes, we have a negative correlation, but we have a weak negative correlation. So what we see on the screen is a kind of a weak negative correlation. So that's the inference that we are able to make right now. So this is how we can study the relationship between different variables. I want to just add one small pointer that correlation does not imply causation. So in all these examples, we are studying two variables, bivariate analysis, two variables. We are looking at correlation, we are looking at relationship between two variables, but remember, correlation does not imply causation. So although you can say that, temperature, sales, and ice cream are correlated, so we can say that more the temperature, more the ice cream sales, which is very logical, right? So as it gets hotter, people tend to buy more ice cream, and we are getting more ice cream sales. It's logical. We can say they are correlated, they are related variables, but we cannot say one is causing the other. I know it sounds logical, but you cannot make the argument that X is actually causing Y. So just by looking at a correlation, we cannot say that because the temperature is more, the ice cream sales is more. So just by looking at a scatter plot, you cannot infer causation because, honestly, howsoever, because the other argument is also possible. You can always say that because people are buying more ice cream, they have to be manufactured, and maybe there is more population, pollution, whatever, and there is more temperature. Okay, the temperature of the earth is rising gradually because of that. Okay, so because of more consumption, right? So something like that, because remember, ice creams require refrigeration. So maybe the counter argument could be that because you're buying more ice cream, not the other way, like because there are more sales, because there are more ice cream sales happening, people are buying more ice cream. Maybe they are coming back home and they are uh, preserving the ice cream, and that means they're buying more refrigerators, and consumption is increasing and all that, right? So that is leading to a rise in temperature. So the counter arguments are also true. Maybe one of the best examples will be this one. Look at this. This is step count versus weight, right? We are again very similar kind of use case. Think of one of these smart band devices or health smart, smartwatch kind of devices that you're wearing, and they're constantly tracking your sleep pattern, your step count, and all that throughout the day. So if you, let's say, look at the relationship between step count and weight. Let's say we are looking at the relationship between the step count and the weight in any one of these devices. We will see an inverse correlation. We will see an inverse relationship between step count and weight. We'll typically see that more the step count. Okay, we will typically see that more the step count, lower the weight. So that is the pattern we will make out. Okay, as the step count increases, the weight reduces. That is what is expected. Remember, it's not causation, it's a correlation. You're expecting that as people take more steps, they tend to lose weight. Those people typically have lower weight because we are expecting that as you take more steps, as you keep yourself healthy, you will not become obese, right? You will probably stay in shape and you will lose weight. But the counter argument is also true. We can always say that because you're already having a high weight, that is why you're taking less steps. Maybe because that is preventing you from taking more steps. You see what I'm coming? So you can say that because X is more, Y is less. Or you can also say because Y is more, X is less. Both are true. So if just by looking at the plot, you cannot say for sure which is causing what. So correlation is not a causation. Remember, please keep that at the back of your mind. So any use case you work in data science going forward, whatever use cases we do, we talked about that beautiful use case of network parameters versus network intrusion detection. These are all correlation use cases. It's not a causation use case. You can never say for certain that because the network parameter is this, the intrusion happened. No, we are only looking at relationship. We are only trying to associate. We are only trying to say that, okay, this and this are happening together. So next time I see a similar pattern, this I can predict. And it's all about pattern discovery. Because the moment you talk about causation, you have to do a proper experiment. So data science and machine learning is all about pattern recognition and correlation, not causation. So these are two very, very different terms. Okay, causation is a proper experiment. So for example, if you want to uh, perform a causation experiment on this thing, if you want to perform a causation experiment to prove that step count indeed reduces weight, let's say Samsung Galaxy Watch wants to conduct an experiment. They want to conduct a, a social experiment saying that if you take more steps you actually lose weight. So if they want to do that, then they will have to do it in a proper experimental setup, which means taking a sample set of people, 50, 100 volunteers they will take, put them through the same facility. Maybe they will keep them in a facility for 4 to 5 months. They will monitor them. They will give them the same diet. They'll keep them the same, living conditions, and you will subject them to the same living conditions and everything. So the idea is to keep every other variable constant. So the moment you are trying to prove causation, you have to keep every other variable constant, which even like goes down to the kind of food you eat and the kind of place you live, right? So even that you have to keep constant, because if we change that, if we make that variable, then there are other factors that are coming in. So that is how a proper experiment is conducted, right? You keep every other factor constant, you modify one variable, and then you see how it changes the other variable. And in fact, that is how your clinical trials also happen. Clinical trials are, the causation studies happen that way. You take a sample set, you take a and that's how you do clinical trials, right? You keep the different parameters, you monitor, you keep different parameters constant, and you see that, okay, when I administer this dose of medicine on this person, this is exactly the change that is happening. So by keeping everything else constant, you're monitoring that by giving this medicine, this is what happened, and by giving this medicine, this is what happened. That is how a lot of these weight loss medications, diabetic medications work out. So they're very, very careful clinical trials that happen. It's not like you're just based on causation, you're saying, okay, you take my drug and you will lose weight. But no, I mean, the moment you talk about some reputed body giving clearance medicines, they go through proper causation trials. Okay, but a large part of data science that we see today, and a lot of the problems and exercises that we will solve, is purely based on correlation, right? So this is a very conceptual thing, and this is what I meant. Like, as we study, you need to be very clear with how you need to study, and this is also part of what I'm trying to do. Okay, because oftentimes, we just study because we have a course or we have some session where we just study, but sometimes it's very important to know how to study, right? So this is the way you should study. So try to have a very good grounding of the foundations, but you don't need to necessarily know how to do correlation, because now that you have the grounding, now that you know what is correlation, you can always go to Gemini, type some code, write a prompt, and it will generate the entire code for you. Okay, so this is useless, this you don't need to memorize, but this is important. That's the difference, right? You should know what these ideas are. So because if you know these ideas, you can always go to Gemini and you can prompt it to write this in a certain way. Okay, now let's come to the meaning and the interpretation of the graph. So what we are trying to predict is sales, right? We are trying to predict sales. Sales is the output variable. And what are the input features? We have TV, we have radio, and we have newspaper. So based on the TV, based on the radio, and based on the newspaper, we are trying to predict the sales. Okay, so I repeat again, based on the TV and radio and newspaper, we are trying to predict the sales. So that's the sales prediction we are trying to do. And when we generate the correlation matrix, this is the individual correlation values. In fact, you can actually plot the correlations also. So if I just go and take this, if I just say data.core, I will just say copy selection, maybe create a new cell. This is how you can create a new cell, and I will just paste it. So when you do this, you can actually get the entire correlation table, right? This is what data.core will do. So data is the entire table, that is the entire data frame which I had. And when I say .core, it will give me the it'll basically give me the complete the complete uh, the complete table, which highlights all the correlations, as you can see on the screen. And all that we are doing is we are wrapping it in a heat map. Okay, the heat map is just kind of wrapping the whole thing. So for example, this is the relationship between TV and sales. This is the relationship between radio and sales, 0.57. It's a moderately positive correlation. And this is a weak positive correlation, newspaper and sales, very close to zero. So this also tells you that newspaper is a bad predictor of sales. Okay, so this is also telling us that newspaper is a bad predictor of sales. If I at all have to go and do a sales prediction use case, newspaper is not the kind of feature I would like to use, because maybe that is going to add noise to your data, and sorry, to your model, and you will not end up having a very good quality model. And I'll talk more about noise and overfitting and all these things later. But just remember that the initial thing that we should do as a data scientist when you get a data set and you start working on it is to identify features which are good predictors of the output, and correlation is one of the first things that usually comes up. And there are other ways to do it. We'll look at some other methods when we talk about more advanced algorithms. What are some other methods around it? But this is the most obvious way to look at it. The most obvious way how you identify based on certain inputs which are the best predictors of the output. Okay, and you take only those inputs forward. So now going forward, you only consider those inputs to predict the outputs. You don't consider the other inputs. So the two things you achieve. One is you end up only taking important features, and second is you only you end up removing features you do not require. So you end up reducing the size of your data. So if you have, let's say, 100 input variables, all the 100 input variables are not important predictors of sales. So you don't need to consider all the 100 input variables to predict the sales, not required. So what you can rather do is you can only consider those many variables that are important predictors of sales, and you can drop the rest. So that's the way how we can excuse me, how we can think through it. Okay, so moving on, this is the correlation part that we did. So I think, so the takeaway, as I said, is that TV is a good feature, radio is a reasonable feature, but newspaper is definitely a bad feature. And going forward, when we build the linear regression model that we will shortly, we will actually eliminate these two features. No, we will not consider these other two features. We will only use the, so we will only use the TV and the radio feature for our analysis. We will not be using the newspaper feature. Okay, now let's move on. As I said, there are a lot of other things I've done which I will skip for the time being. We'll come to these pieces later on as we go along. Now let's come to the actual modeling part. And this is the very first machine learning model that we are building. It pretty much summarizes everything that we talked about so far in terms of machine learning. So all of you can see the screen. This is the most basic machine learning model that we have built so far. This is our first machine learning model. And again, you can see we are using a library called Scikit-Learn. Scikit-Learn is the a slightly new library that we are seeing on the screen. Scikit-Learn stands for Scikit-Learn. Okay, so Scikit-Learn basically stands for Scikit-Learn. It's a library which helps us work with all the different machine learning algorithms and anything and everything related to machine learning. It's algorithms, the different machine learning tasks, the different types of pre-processing operations that we do on the data before we start applying the algorithms. All that is present inside the Scikit-Learn library. It gives us all the tools. All the tools are available, and it's one of the most popular libraries in Python out there today as we speak. Next, I have separated the X, separated the Y. This is the straightforward stuff. This is my X is my TV, Y is my sales. And now we actually go ahead and start building the model. But before we go to this part, we have just one more level of detail to cover. I think otherwise you can see the code is very simple. There is nothing much to talk about it, but just one small level of detail which we haven't talked about. What is that, friends? So we do not know this part. This is the part we don't understand. Everything else we understand. We have discussed linear regression. We have discussed model parameters. We have discussed coefficient. Let me just kind of uncomment this part out. We have discussed all these pieces, right? We know what is M. We know what is C, model parameters, slope, intercept. We know everything. But something we don't understand is train test split. And at this point of the session, what we will do is we'll take a small 5-minute digression and understand what exactly is machine learning from a slightly technical perspective. What is machine learning? What are we actually trying to do? I know we talked a lot about it. We know what supervised learning, we have inputs, we have outputs, we are using some algorithm, learn the patterns, all that we have done. But now let us understand technically what is going on in machine learning. How do we actually build a machine learning model? what is training, what is testing, how do we build the model, how do we evaluate the model on the training data, the testing data, and all the different pieces related to that. Let us see that in action. Before I explain it, all of you just give it a glance once. Just give it a glance once for a minute, okay? No need to understand. I'll explain to you, but just give it a glance. 2 minutes. Just give. Then I'll explain. So, one way to understand this workflow is through an analogy. It's always good to learn new concepts. Always try to learn them through analogies, so it helps the concepts stick a lot better. You tend to remember the concepts a lot better when we take analogies and diagrams. So one way I would like to explain this diagram is through the analogy of an examination process. So imagine you are trying to prepare for an examination. So the objective is that you are trying to prepare or study for an examination. And what, how do you study? How do you prepare for an examination? When we talk about a typical examination process, how do you prepare? How do you study for an examination? So what you do is first you study and you prepare very hard from your textbook. Okay, so first thing that you do is you prepare and you study very hard from your textbook. And next what you do is you go and you practice a mock question paper and you evaluate yourself on the mock question paper. Right? I think everyone can relate to it. These are the broad steps that are involved, right? So the first part is we go and study very hard on our textbook. So we study the concepts, we study the topics very, very hard on the textbook data. And second is we go and evaluate ourselves on the mock question paper. So we evaluate ourselves on the mock question paper. So whatever test paper we have, whatever question paper we have, we evaluate ourselves there. That's the idea. And then we write the final exam. So if we are good in the evaluation, so the final 1 week or 2 weeks before the exam, we write a mock question paper. And if we score reasonably good marks in the mock question paper, that means that okay, our preparation process was good. And if we can be confident that yes, our preparation process is good, if we can be confident about it, then we can go and absolutely uh, use our learnings to write the final exam. So that's the way how we can typically go about it. Now let's try to connect the dots and understand how exactly this is playing out here. Okay, how exactly this entire piece is playing out here. What I'll do is I'll just take a small snipping tool to explain this a little better. So, and then we'll connect the dots and try to use this in the code. Okay, so we'll see how the code looks like once I explain this, the core idea to all of you. All right. So let me hide this part for a minute. Don't worry about this YP, YA, what is it? I'll explain all this to you. Hide this for a minute. Also hide this for a minute, okay? Now, what you have here to start with is you just have your data. You have the complete data that is available, which is a bunch of XY combinations. right? So you have the complete data that is available, which is a bunch of X, Y combinations that you have right now. So you have X, you have Y, X, Y combinations, 1, 1, 2, 4, 3, 9, 4, 16, 5, 25. This is the available data that you have right now. And the first thing that we are doing is we are splitting the data into training and testing. So what is the meaning of training and what is the meaning of testing? Training data is usually textbook. So training data is usually our textbook. Textbook is what we are studying from. So we will learn the patterns from our textbook. That is usually what we call the training data. So what is the training data? Training data is usually part of our textbook. We will learn the patterns. We will learn the patterns based on the we will learn the patterns based on the training data. We will learn the patterns based on the textbook. And then we have something called the question paper. The question paper is the test data. That is what we will evaluate ourselves on. So these are the two important pieces. One is the training data. The training data is what you will study from. Okay, so you will study the patterns from the training data, and based on whatever you study, you will evaluate the patterns on the basis of your question paper. Okay, so that's the idea. That's the core idea that we have here. Now, so here, once we split the data, we have training data. You can see 1, 1, 2, 4, 3, 9, 4, 16. So that's the data that is present as part of my textbook. And remember, this is what we will use to train the model. When we talk about model training, this is the data that we will eventually use to train our language. We will train our machine learning model. Okay, so this is my textbook. One, because when we study, when we are in the initial preparation process, we need the outputs. We need to know the examples, right? Examples are what? Examples is nothing but a combination of lots of inputs and lots of outputs. That is what examples actually are. So when we talk about examples, examples are nothing but lots of input output combinations, lots of X's and lots of Y's. That is the example data, right? That is what we refer to an example when we say example, right? So this is my example data that you can see on the screen, X and Y's. Lots of X, Y combinations we have here. That is part of my example data. Now the concept is we will use some algorithm and we will build a model 1, 1, 2, 4, 3, 9, 4, 16. You will use a linear regression algorithm, do a best fit line, and you end up building a mathematical model. Let's say this is actually not linear, it's polynomial regression. It's a non-linear model, y equal to x squared. That's a parabola that you're getting. Anyway, so you've basically learned the patterns between x and y as part of your textbook. So in the textbook, the patterns are y equal to x squared. Now that you understand this pattern, now that you understand that this is the pattern that is playing out in the textbook. So now that you understand that this is the pattern that is playing out in the textbook, you will use that pattern. Now we will use that pattern and use that to solve a mock question paper. So we will use y equal to x squared and we will use y equal to x squared to solve the mock question paper. Whatever learnings we got on the textbook, now we will use those learnings to solve the mock question paper, which is uh, the testing data, the mock question paper. So here y is 5. So sorry, x is 5. So when x is 5, what is the predicted value of y? You know x is 5, 5 square is 25. So predicted value is 25. This is what we do as part of evaluation, right? So when we solve a test paper, what do we do? So we have already learned something, we already studied something, and now whatever we have studied, we want to apply our learnings in some new data set, right? So whatever we have studied, we want to apply our learnings. We want to apply our learnings on a new data set. So when x is y, you want to predict, okay, hey, what is the predicted value of y? That is 25. That's what you're getting right now. Okay, the predicted y is 25. That's a test accuracy. So now you can monitor and you can find out the test accuracy. What is the test accuracy? So when you're solving the mock question paper, what do? You answer the questions. That's my predicted y. And then you will compare the predicted with the actuals, which is also 25. So we are having 100% accuracy, isn't it? See the analogy, what I'm trying to explain to all of you. So you studied something and now you are evaluating what you studied on some completely new unseen question paper. You are evaluating what you studied on some completely new unseen question paper. And by doing that, we are still getting 100% accuracy. We are still getting 100% accuracy. So the overall accuracy of the model that we are getting is 100%. And that is what we call test accuracy. So similar to test accuracy, we also have something called training accuracy. And what is training accuracy? What do we mean by train accuracy? So train accuracy is like revision. See, oftentimes when we study and when we prepare for something, one part is we solve the mock question paper before the exam. Another thing that we usually do is we go back to the same textbook, isn't it? Oftentimes we do it as part of our preparation. We go back to the same textbook, and by going to the same textbook, we often solve the same problems from the textbook, and that is what we do as part of revision. And as part of revision, what we will do, we will again hide the actual question answers. No, this is what we do, isn't it? We hide the actual answers, and now we start to answer the textbook questions using the same learning that we got. So using the same learning, whatever learning that we got here, now we will start to attempt the textbook questions, and x is 1, predicted y is how much? It is 1, 2, 4, 3, 9, 4, 16. Look at this. And now we will compare with the actuals, 1, 4, 9, 16. So okay, this is amazing. Amazing. The learning is amazing right now, because based on whatever I prepared, based on my preparation, I am able to solve. Based on my preparation, I am able to solve the unseen question paper with 100% accuracy. Okay, so purely based on my preparation, I am able to solve the unseen question paper with 100% accuracy. There is 100% accuracy I'm getting on the unseen question paper. And even on the training data, the textbook, I'm also getting 100% accuracy. There is 100% accuracy I'm getting on the unseen question paper, and there is a 100% accuracy I'm also getting on the training data. So this is a very good quality model. And now that we are confident about the ability of this model, what I will do, I'll deploy it. This is the deployment part, which we'll see later on. So we'll deploy this model, and we will use this model for the final exam. The final exam is where we will use the algorithm, the same algorithm that we learned, right? The same model that we learned right now. So final exam is going to be something like this. They will ask you some question, x is 6, and based on 6, you will say 6 square 36. Try to predict the y. So this is the workflow of machine learning, right? So you can see the few core aspects that we discussed here. We take the data. We always split the data into two components, with something called training data, and there is something called testing data. Okay, so we take the whole data and we divide the data into two components, training data and testing data. We build the models on the training data. So whatever training data we have, we learn the patterns on the training data. Okay, so we build the model and we learn the patterns on the training data. And based on whatever patterns that we learned on the training data, we go and evaluate those patterns on the testing data and calculate the accuracies. Okay, so this is the workflow, and now we are simply trying to incorporate this workflow in this hands-on. So if I just try to show you on a split screen side by side, you will get a better idea of exactly what we are doing. So until here, I think we are sorted. So we have taken TV, we have taken sales, and this is an example, right? You might be questioning that, okay, Shine, why have you not taken radio? Why have you not taken newspaper? I will try it out. Right now, I'm just starting the conversation with just TV, because remember, we saw that TV was the best feature. You always start out with the features which are the best, and then you progress to the remainder of the features, because one of the things in machine learning is that it's always very, very, it is always it's always exploratory. It is very experimental in nature. You will never know for sure whether something will work. So here we think that TV is the best feature, and with TV we'll get the best model. So this is something we assumed, is something we think, but that may not always be true. So here also we think that okay, TV is the best feature, but it may not always be true. All right. Anyway, so we have the TV feature. We are trying to predict the sales. We have selected these two variables here, X and Y. So this part is sorted. And this is the important part. We are doing a train test split, you can see. And this is the code. So X comma Y, test size equal to 0.2. And what it means is when I do this train test split, see, we are splitting our data into X train comma Y train, X test comma Y test. I mean, if you think of it pictorially, all that we are doing is we are taking the X comma Y. This is my X comma Y in my data frame originally that we had. And we are splitting the data into X train, Y train, X test, Y test, not the predicted. Please remove the predicted part. That is not important. So this is my X train comma Y train. And this is my X test comma Y test. So we take the X, Y, and this is X test, Y test. And this is X train, Y train. That's what we have done here. And I think the next part you can understand. Now we are using linear regression model 2 on X train comma Y train. So whatever X train, Y train that we have here, so we are simply trying to apply the linear regression algorithm on the X train comma Y train data. And once we do that, we will end up with a mathematical equation. So when I do model 2.fit X train comma Y train, that means on the training data, I'm trying to fit a linear model. I'm trying to find that line of best fit. And these are the parameters of your model. Okay, so this is the slope and intercept of your model. So this is like the coefficient is the slope and the intercept is typically the y-intercept. So whatever model 2 that we fit here, you can actually find out that what is the coefficient and what is the slope of my model and what is the intercept, the y-intercept of my model. So you can see that this is the equation I'm getting. And if I have to write it down, the corresponding equation is it's actually somewhat like this: is sales equal to 0.04 times TV plus 6.79. That is how the equation looks like right now. You can clearly see the slope is 0.04 and the intercept is 6.79. So this is the slope and intercept of my model. So that's the way how we can relate to it. So you can see how interpretable the things are. So once you have the data, you can easily fit a model. And now we can also see exactly what is going on behind the scenes. And we can also interpret that 1 unit increase in TV advertising. So if you spend $1 more on TV advertising, the sales on an average will increase by $0.04. That is a pretty powerful thought, right? So if the TV advertising sales increases by $1, if you spend $1 more advertising for TV, the sales will increase on an average by $0.04, which is a pretty powerful thought. Pretty powerful thought. And also 6.79. What is 6.79? 6.79 tells you that okay, even if you spend nothing on TV, even if you spend absolutely nothing on the advertising expenses, even if you spend nothing on the advertising expenses, you will still end up making 6.79 units of sales. Okay, so that is the 6.79 that we're getting here. So even if you spend nothing on the TV advertising, you will still end up getting this much amount of sales. This is the overall amount of sales we will still end up getting, even if we spend absolutely nothing on the advertising. Maybe due to the brand recall or some of those other factors that we can say. And once we did that, now we can go and this is the model that we trained. We have seen the model parameters, how we can relate to the model. And remember, there was only one X. So we can obviously, if we take multiple features, we will have multiple parameters. And finally, this is my training and testing accuracies. R squared is another indicator that we use, but don't worry, that's a technical thing. R squared stands for coefficient of determination. This is a typical accuracy metric that we use for regression problems. Okay, but just for the time being, just for simplicity, you can think of this just like accuracy. So what is R squared? R squared is just accuracy. This is the accuracy of the model. Okay, so R squared is nothing but the accuracy of the model. So that's the way how you can relate to it and how you can think of it. So R squared is the accuracy. That's what you can look at here. Okay. And the baseline model that we have built, the training R squared is 63.93%. And what is the testing R squared? It is 41.53%. So this is the baseline model that we have designed right now. You can see. So, so whatever model that we have built right now, the training accuracy and the testing accuracy both are pretty low. Okay, I think you can clearly see that in this model, the training and testing both are pretty low. So training accuracy is also very low, and the testing accuracy is also fairly low. So we have a very basic model to start with. Okay, we'll introduce some new jargons as we go along, but it's actually called an underfit model. But this is a very poor quality model to start with, because on the training data also we're getting a very low performance. That means it's like saying you have not studied well on training, right? So when I was teaching you something, when we were learning some new topics, you didn't study well from the textbook, so you're struggling there. And even when you're testing, when you're evaluating yourself on a unseen question paper or a mock question paper, you're struggling there also. So training accuracy is also low, testing accuracy is also low. So this is what we are able to see here. So this is what we call an underfit model, very poor quality model. And now we can compare. Okay, so now this is our very first machine learning model, and now we can compare. And you can see there's something called model.fit we use. So we've talked about it in the beginning of the session. If you remember, I told you that this is what we do as part of model training. So next time when we talk about training the machine learning model, we are using model.fit. So this is that model.fit that we are actually kind of using here overall. So as part of model.fit, you can see that we take the data and we are able to create the create the machine learning model, and we are able to evaluate the accuracy of the machine learning model, and this turns out to be a highly underfit model, very poor quality model. And now we can incorporate the second feature. If you remember, after TV, radio was the most important feature. So now we can experiment, but this is the process of experimentation. Okay, so this is the process of experimentation. So now we can incorporate uh, the radio feature, and now we can take both the TV and the radio feature, and we can check how the model has improved if I consider both TV and radio. So when I consider both TV and radio, we can run the code. Everything will remain the same, nothing will change, and we can comparatively see that when I incorporate both these inputs, whether I'm able to build a better quality model or not. So we can just run the code again, and you can see that we've got a better quality model because the training accuracy is higher and the testing accuracy is higher. Isn't that what we want when we are learning something? Isn't that the objective? Because when we learn something well, ideally we should perform better in the training. It's like saying, if I ask you some questions in the class, if you're listening to what I'm saying, if you're hearing what I'm saying, everybody should be able to answer what I taught you today, right? But at the same time, if I give you some exercises, which we will start with in the next phase, we'll do some exercises. If I give you some new questions, you should still be able to answer that. So both are important. So training accuracy means how well you are able to understand what I'm teaching you. But can you remember what I taught you? Can you solve the same exercises? Like if I give you the same problem, can you solve it? That's training accuracy. Testing accuracy means if I give you a different data set, can you solve it? I mean, that's like generalization. So I mean, you don't just memorize and like remember what I taught you. You don't memorize it. Like night before the exam, you memorize the topics. That's useless, right? But you understand what I taught you. So if you understand what I taught you, then even if I give you a different data set, you'll still be able to answer it. So that's the whole idea. And this is the concept. And this is what makes machine learning a very highly experimental domain, because you see how we're experimenting with different features. So we started with only a single variable called TV. Then we took more variables and we tried to build different models in a very exploratory manner, and we are trying to see which one is better. See the idea? And initially, I was talking about Jupyter Notebook. See how this is. You cannot script it out. So when you're doing model development, you can't just write a single Python script up from scratch. You need to run the code. You need to execute multiple blocks, see which one works the best, where you're getting the best scores. Once you're confident, then you will transform this into a script. So this is why the exploratory development mode that Jupyter gives you is very, very helpful, because you try out different things. Maybe here, let's say I've got two features, TV, radio. Maybe you feel the need that I need to create a new feature. And oftentimes in data science problems, you might want to create a new feature, a new calculated feature, something, some kind of a computation, some kind of a calculation using two or more features. You create a new variable. Okay, and you want to use the third variable. But you have a hypothesis. You have a hypothesis that, okay, I think the third variable is a good feature, but you don't know that yet. How do you test it? How do you test your hypothesis? So you create the third feature. You create a new feature called, let's say, X3, and X3 is some kind of mathematical computation of something, whatever. You create a new feature called X3, build the model, and compare the accuracies. See the train accuracy, see the test accuracy. So did it improve the model? If it did, well, wonderful feature. It's a good feature. Because remember, we are always working on correlation, not causation. So if you are able to create variables, if you're able to find correlation between the inputs and the outputs, and if that leads to a better model, that's all that we look forward to. We are ultimately trying to create a good quality models. This is the model.predict we can do. So if you see my code, this is the prediction. So if you want to do a prediction, you can just do model.predict. So there are two parts to it. One is .fit. .fit is how you build a model. You can try different algorithms, and you can do a fit. You can build a model, and you can go back and do a .predict. Okay, if you want to evaluate you want to use that model for a new data set. If you have a new value, you have X new, and you want to do a prediction, you will simply do model.predict. Right now, what I want to do in this part of the conversation, I want to also show you how easy it is to use a different algorithm. Okay, so what I did in this part of the code is I used something called linear regression. It's the most basic algorithm that we are starting out with. One of the other things about linear regression is that it is usually um, it is a very baseline model. Think of it as a very, very baseline model, and it's absolutely possible that for certain types of data, it may not give you very good results. Right. So here it's a very simple data set. We have input X, we have output Y. It's a very straightforward data set we are working with. So linear regression did give us 80% and all, but as I told you, there can be certain types of data patterns which are inherently nonlinear. And if you're dealing with inherently nonlinear data patterns, then linear models will not work. You need nonlinear algorithms. And for that, we can try out different algorithms and see which algorithms are giving us the best results. So there are mainly two core ideas that we are working with. If I just switch the conversation to some of the things that we discussed, some of the things that we did. So there are broadly two core ideas, if you see. So one is we are trying to take different variants of data. So we are trying to modify the data. This is exactly what we did, right? We tried to take a different data. We have TV and sales, and we tried to create, we tried to take TV and radio, and we are trying to modify the data in different ways. We're trying to select the most important features, remove the least important features. Like if you remember, we did not take newspaper. That is one part. We are trying to modify the data, keeping the algorithm constant. Now what we will do, and we achieved some success. I think you saw that when we took TV and radio, we got a better result by taking the same algorithm. Now what we'll do is we'll keep the data constant, but we'll modify the algorithm. We will use a more powerful algorithm. Right now I use linear regression. Now I'll give you another demo where I'll show you gradient boosting, a more non-linear algorithm, and with that I will get a better result. So the objective is to build a good model. And what are the two components of a model? Data and algorithm. Okay, so you can use a better quality data, or you can use a better quality algorithm, which is more robust, which is able to represent the patterns in a more generic way, or you can use a combination of both. And this is the experimental part of machine learning I was talking about. This is the part that takes the most amount of time. And as we go through all the case studies, and lots of case studies we will see as we go through the sessions, as we go through all our case studies, I think this is one area that we will try to cement. I think the having the right thought process, to think of exercises in this manner. So how can you look at a wide variety of problems? How do you figure out what kind of data to take? how to try out different algorithms. And this is the exploratory part. Okay, so you try out different permutation combinations, and you narrow down to the ideal set of data and algorithms. And once you and build the final model. Okay, so here let me give you an example of using a different model. So I think until here we already did. So just to clarify, just to compare the results, I think we are pretty sorted with this part. See, we separated the data, use linear regression, training accuracy, testing accuracy. So we are sorted. Now what I will do, I will use the exact same data. I don't need to do X-train, Y-train anymore because that's the standard. I will use the exact same data, and I will just use a different algorithm called, I don't need to type out, I can always use Gemini, but that's okay. I think this is, I think once you do some practice, this is becomes back of the hand stuff. It's a regressor actually. So, and I'll just say from sklearn ensemble import gradient boosting, look at the magic. Can you see the magic? So Gemini understands, look at this. I mean, it's almost incredible to even talk about it. Gemini understands what I'm trying to do. Can you see? So it understood in the previous cell, I was actually showing you a demo of linear regression. So, and Gemini somehow understands. Gemini is Google's language model. So it somehow understands the context. It understands that in the previous cell, I was building a model using linear regression. And the moment I import gradient boosting regressor, it understands that, okay, most likely Cyan is trying to do this. Most likely Cyan is trying to replicate exactly this pattern, this time using gradient boosting. Okay, it guessed it right. That's fine. And if I hit enter, it will further give me the testing. Can you see? Incredible, isn't it? I didn't type a single line of code, by the way. It's all generated by Gemini. Anyway, so now what's going on here? So we have the same X-train, Y-train, X-test, Y-test, because remember, my training and testing data is the same. Okay, so my training and testing data is the same because we have the same textbook and we have the same mock question paper. We have the same textbook and we have the same mock question paper. So this is my training and testing data that we have, and only thing is that we are using a different algorithm. So the only thing right now is we are using a different algorithm. So you can see that we are using a different algorithm here, and we are using something called gradient boosting regressor. So this is a different algorithm that we are actually using right now. And look at the magic that will happen right now. The moment I use a different algorithm, you will see that my results will be a lot better. I will get a lot better results. So control enter, you will see 99% and 97% straight away. Okay. It sounds magical, but what is going on behind the scenes is actually non-linear regression, because all this while we discussed about linear regression. So what you are seeing on the screen right now is actually non-linear regression. So it's not trying to find the best fit line, but it's in a way trying to find a kind of a non-linear mathematical surface. That is what is doing behind the scenes. So this is the big part of what we'll try to do in real world scenarios also. When we build machine learning applications, you will have to constantly look at your data, figure out what are the different types of features you can take, identify flaws and defects in the features. There can be some missing values, outliers. So try to clean your data. So that is also a big part of what a data scientist will do, right? And honestly, much of these tasks have become very commoditized because with language models like Gemini and Copilot and so many easier ways of getting things done. So there are libraries that we have for everything today. But yeah, but this is just to show you a flavor of how things are done. You try different models, you find out their scores, you try a different algorithm for the same data. A different algorithm is giving you a better model, and this is a much better model than what we had before. So this is what and there are many. There are other algorithms you can also try out. For example, I can maybe create one more code cell, and this time I want to use. Okay, you know what? You don't even have to type out. Just go and use a comment line and say, uh, build a model, build a model using random forest classifier. So in case you forgot what is the syntax to import, even you forgot the import syntax also, so you can actually say, build a model using random forest classifier, using random forest. Sorry, not classifier, regressor. And if you just do this, wow, amazing, right? Gemini will even do the import package for you. So last one, I at least took some effort to write the import package. So here I just put a comment line. build a model using random. And see, this is not a random response. It's not a random response. It actually gives the response with respect to my code. It is not a random response. If you see, even the variable names are the same. Even the model 2 is exactly what I used. And that is why I say it's very powerful, because it's so the code editors of today are very context sensitive. They're context sensitive and they understand the code base. And the moment you try random forest, you see it's even better. The test R square or the test accuracy is even higher, 98%, which is great, right? So this is the way we iterate. This is the way how we, as I said, we try out different variations of data. We try out different types of algorithms, and we try to figure out which algorithm is actually giving us the best results. And I think based on what we saw here, the random forest regressor is giving us the best model, because the test accuracy of this model is the highest. We're getting 98.61% test accuracy. That's what we're getting. There are some further concepts that we will study along the way, but before we get any deeper, there is one more very important topic, important concept that I've generally discussed, but I want to kind of cover it a bit more conceptually. Just this is a 5-minute concept that we will see: overfitting and underfitting. I might have mentioned that term a couple of times already, but let us understand that a bit more in detail. What is overfitting and what is underfitting? We are able to see overfitting and underfitting uh, being explained in this particular diagram. On the left hand side, you see model error. So error is nothing but 1 minus accuracy. So that is how we understand the meaning of error. You can see this is 1 minus accuracy. And along the x-axis, you see something called the model complexity. On the left-hand side, you have a overfit model, underfit model. And on the right-hand side, you have something called an overfit model. So what is underfitting? What is overfitting? So underfit model is that kind of model where there is no learning happening. That is what we refer to as underfitting. So what is underfitting? Underfitting is a condition where there is absolutely no learning happening. That is what underfitting is all about. There is no learning happening in underfitting. The training error is also very high, and the testing error is also very high. So both the errors are high. The training error is also high. The testing error is also high. So both the errors are high in underfitting. So there is no learning happening, right? Obviously, you can imagine that it's something similar to this we saw when we tried to build a model using TV and only the TV feature. So when we built the model using only the TV feature, we saw something very similar to underfitting happening, right? That's what we saw. What is overfitting? Overfitting is where the training error is very low. That means you learn the patterns very well on the training data. On the training data, you learn the patterns very well. But on the unseen test data, we make lots of mistakes. That is how we define overfitting. So underfitting is where both the errors are high. So training and testing, both the errors are high. So the model performs very poorly on training, very poorly on testing. Overfitting is where the training error is low, testing error is high. So that means it's kind of like rote learning. No? Rote learning is where we memorize something in detail. We try to memorize something. Rote learning. So you learn the training patterns very well. You don't make any mistakes here. So training error is zero, almost close to that. But have you really learned anything? Maybe not. If I give you a new exercise, you struggle. Even test data, you struggle. So that's overfitting. Both are bad. So what we need is we need to create a good fit model. And good fit is that zone where we have the lowest test error. Lowest test error basically means the highest test accuracy. So when we have a model with the lowest test error, that means typically the test accuracy is the highest. That is what we mean by having a low test error. So low test error basically means we have a high test accuracy. So this is the objective of machine learning. So we try out different permutation combinations of data. We try out different permutation combinations of algorithms. We try out different algorithms. We try linear, we try random forest, gradient boosting. We try different algorithms, and we'll see that in a lot more detail. We have a lot of way to go. And we build different models, and then we evaluate which model is giving us the best performance. So we have model 1, which is giving us this much accuracy. Model 2 is giving us this much accuracy. So we compare the performance across the different models and we see which model gives us the best performance, and we try to build the most good fit model. So that's the way how we go about it. Now, if you relate this to what we discussed in our uh, conversation already, you can see we started our conversation with the TV feature. And if you remember, when we built the model with only the TV feature, we were getting a highly underfit model. Why were we getting a highly underfit model? Because the training and the testing scores both were extremely low. The training score was also very low, and the testing score was also very low. So that is what we refer to a highly underfit model. Then we took TV and radio. If you remember, we were getting something like 60%, 40%, highly underfitting. And now we take radio feature. We take one more feature. And when we take that extra feature, we are getting a better quality model, right? You can see the training score is also high and the testing score is also high. So by incorporating that new feature, by incorporating that one extra feature, we are able to build a better quality model, a more good fit model. If I have to be more technically correct, we are able to build a more good fit model. This is what we call a more good fit model because we are getting a higher accuracy in training and a higher accuracy in testing. There is another very important concept I would like to talk about, and the concept is related to so the concept in this case is related to the idea of um, the relative performance. So overfitting and underfitting are both relative techniques. So when I say that we are trying to build a good fit model, remember the good fit is always relative. So we are always trying to build a model that is relatively more good fit. That is the core idea. There is nothing called absolute good fit, but we are always trying to make it better. We are trying to always build a model that is relatively more good fit. And that is an important idea that I want to clarify. So imagine here I'm getting 89%, 89%. This is the same thing I was demonstrating here, right? If you remember, we got with linear regression, I was getting 89% and 89.47%. We got a decent model, right? Anybody who sees this model in the first glance, they will say that, hey, this is a good quality model. It's a good it's a good fit model. But you know what? This is not the best model. We can make it better. That's what I mean to say. We can make it better. So we can take this particular model and we can make it better than this. It is always relative. The idea is always relative. So with gradient boosting, if you see, compare this with this is what we call a more good fit model. Because the training score is higher, the testing score is higher. So in both the parameters, you do better. This was already a good model. It was a decent model. But the next model that we built using gradient boosting, keeping the data the same, the algorithm is different this time, we are getting a better quality model because the training score is higher and the testing score is higher. And that's the way how we understand the concept of overfitting, underfitting, and good fit. These are some very, very common terminologies that you will hear in machine learning and very, very common terminologies that you will hear. I think this is another couple of very interesting diagrams you will find which helps us solidify this concept because this is another way to look at it. All of you take a look at it. This is pretty much what we talked about. You can see on the left hand side we have an underfit model. That's what we are doing in regression, right? We are trying to find the line of best fit. Remember, it doesn't always have to be a perfect fit. It has to be a best fit. So on the left hand side we see an underfit model. Underfit model is where we are not able to represent the patterns perfectly. That is what we call an underfit model. And on the extreme right hand side, we are seeing an example of an overfit model. This is a model where we are actually learning the patterns perfectly well. On the left hand side, we are not able to learn the patterns at all. That is perfect underfitting. On the right hand side, we are learning the patterns too well. So whatever model we are building, it is basically passing through all the points. That means on the training data, it is doing a very good job. And this is what we refer to as overfitting. And somewhere in the middle, we are seeing an example of good fit. Good fit is like an okay kind of model. We are able to like reasonably do a decent job. This is a pictorial understanding of what is underfitting, what is overfitting, what is good fit. And this is the reason why, if you remember, that using linear regression on the sales data set, it didn't give us good results because it was most likely underfitting. Although we saw 89% accuracy, R squared is what we were getting, but still, when we did gradient boosting was doing something like this. It was a non-linear model. It was a polynomial model that we were building. So this is what happened behind the scenes. Okay. Now, moving on. So there are a few other things I've done in the notebook, and I will, as we go on through the topics, we will discuss this more in detail, what exactly this is. But there's another very interesting concept that I have covered here called cross-validation. The idea of cross-validation and an estimator. So every machine learning algorithm, so we did something called linear regression, and then we did something called gradient boosting, and then we did something called random forest regressor. So every machine learning algorithm comes with different types of tuning knobs. And you know what are the tuning knobs? The tuning knobs are basically certain parameters that you can control in the models. So as you're using these algorithms, these are different parameters you can control. So even this has to be tuned. If I use a different value for these parameters, we will not get very good results. So even this kind of thing we will have to basically control. Okay, and these are the tuning knobs that we are kind of talking about here. So when we come to gradient boosting, you can see right now what I've done. I can use different types of values of estimators. This is the same data set, X train, Y train, X test, Y test. I can start with estimators equal to 1. And very interesting, for the same gradient boosting algorithm, for which we got such a good result, the moment I take the value equal to 1, now what is n estimators is something I'm not getting into right now because that's a mathematical thing. We need to study decision trees for that. We'll come to that later. But for now, just remember different algorithms will come with different hyperparameters. They are nothing but tuning knobs. And even that you are trying to control. This is not manually done. There are different tools that you will use for it. So as a developer, when you're trying to build applications, you will have to figure out the right kind of data. You will have to figure out the right kind of algorithm, try out different algorithms and choose from a list. And you will also have to try from the different hyperparameter values. So in this case, you're choosing n estimators, and you will take different values of n estimators and trying to decide which is the best one. So maybe in this case, you take n estimators equal to 1, you get a very poor result. And now you take 2, and you see that as you increase the value, it's like a knob that you tune, right? You can see as you increase it, for the same algorithm, as you take a higher and higher value of n estimators, you see you're getting towards a more and more good fit model. Can you see the training and testing scores are slightly going up? When I take n estimators equal to 3, the scores will slightly go up. When I take n estimators 4, the scores will slightly go up. So as we take different values of n estimators, the scores will increase. Okay, so you can see that when I take an estimators 3, it is 43 and 38. When I take 4, it is 53 and 49. When I take 5, it is 60 and 57. So as we increase the n estimators, the values are actually, the scores are actually improving. The model is becoming better. It's not guaranteed to happen. We have to tune the hyperparameters, and this is how we can uh, choose the ideal value of the hyperparameter. But remember, if you take a very high value of n estimators, this might actually lead to overfitting. What is overfitting? Overfitting is a situation where the training score is very high, but the testing score is very low. So just be cognizant, just be aware of it. Do not take a very high value because if you take a very high value of n estimators, your training accuracy might touch close to 100%. It's also a little slower to run now. Your training accuracy will touch 100%, but your testing score will keep reducing. So this is another thing to keep in mind, that it's a knob that you have to tune. If you make it very less, it will underfit. If you make it very high, it will overfit. You have to choose something in between. And this is a very important thing that everybody should keep in mind as we do a lot of machine learning going forward. Even in deep learning, the same idea will get used a lot. So you'll try out, you will experiment with different types of models, take different forms of data, try different algorithms, try different hyperparameters, build different models, and then evaluate on the basis of this thing. Okay, so right now I'll just set it to maybe something like 100, or we can leave it as a default. So this is something that we need to tune. Okay, just keep this at the back of your mind, everybody. One more very important thing I would like to clarify at this point in time is All this while we were using, and these are all core concepts. Okay, so as we see the demos going forward, the same core concepts will get repeated. Another very important concept I would like to cover is the concept of train and test accuracy, or train and test R squared. Now, we have already discussed it. I know we have already covered what is train R squared, what is test R squared. We know that. We know what is training and testing accuracy. But please understand that whatever we have done now, we have, before we even define the model and everything, we created something called a train test split, right? This is the general workflow that we followed, right? Which we took the whole data, we split the data into training and testing. Pretty much the same work that we covered here, right? If you remember, we take the data, we split our data into training and testing. The problem is there could be bias, there could be some inherent bias in your training data, and there could be some inherent bias in your testing data, right? So what I mean to say is it could be possible, it could be possible that by chance your training data is too easy and your testing data is too difficult. It could happen. I'm not saying that it will happen, but I'm saying it could happen. Because you're doing a random split, right? You are doing a completely random train test split. And because you're doing a completely random train test split, it can absolutely happen that your training data is very easy. So it is very easy to study the topics. But the moment I give you are solving a mock question paper, the question paper is very difficult. So when that kind of thing happens, the testing accuracy and the training accuracies will not give you robust answers. Imagine a real preparation process. Let's say you studied something and you want to evaluate yourself a week before the exams. You want to do some mock sample exercises. You want to do some sample exercises. And when you are attempting the exercises, look at it this way. If your question paper is very difficult, then it won't be the right evaluation. Moreover, it is also important to do multiple evaluations, right? If you are only evaluating based on one mock paper, that is not the right kind of evaluation. So all this while, what I did was I calculated a single training and a single test accuracy, right? So we solved one mock question paper and we saw, okay, I'm getting this kind of a score. I'm getting this kind of an accuracy. But that is not the best indication of the model, right? Best indication of the performance of the model, because what you need to do is you need to evaluate this model on a bigger data set, on a much bigger sample set of mock papers. It is almost like how we conduct an interview in a company. So when you want to interview a person, do you only conduct a single round of interview? Not really, because a single round of interview has higher potential of bias. If you only take a person and ask that person one question, if the person answers the question hired else fired, no, that's not ideal. But you want to, because your test data, it could be biased. So whatever questions you are asking to that person, maybe by chance that person knows all the topics. It could be a fluke hire, right? It could be a wrong hire. So that is the same concept why we do multiple rounds of interview. We take multiple question papers and we solve multiple rounds and we evaluate, take the average. The same applies for machine learning also. So instead of evaluating the model on a single test set and calculating a single accuracy or a single R square in this case, we try to evaluate the performance of the model across multiple train test splits. We try to split the data in different ways. And I'm trying to explain this in a very analogous manner. So imagine we are creating 10 different question papers, and I will ask you, whatever model we have got, I will ask that model, and I will try to find the performance of that model across 10 different question papers. How is it performing in the 10 different mock papers? Find out the accuracies, take the average. And that is kind of something I have simulated here. It's not absolutely perfect, but this is kind of something I simulated here. You can see. Okay, so this is exactly what we can do using something called cross-validation. Okay, so this is exactly something that we can simulate using something called cross-validation. So this is the problem. How do we solve that problem using something called cross-validation? So this is the same linear regression algorithm that I can use here right now. So you can just maybe copy the code and paste it here because this is where we have done the stuff. So let me show you in the same demo. So this is the linear regression part, if you remember. Let me run this code once again so that we are clear. And I will just use that cross-validation code. So until here, we are getting a single training and single testing score, which is not ideal. I want to do multiple rounds of interview. So what I can do is I can take the same model, which is model 2. I will use something called cross-val score. And if I say CV equal to 10, you will actually get 10 different scores. And now what I can do, I can actually take the average score. Okay, so we can say print the mean score, the average score. Okay, so it is actually giving me everything. Can you see how cool is this? Look at this. This is power of Gemini. So Gemini understands what I want to do. So we have done 10 rounds of interview and we have got 10 different scores for the same linear regression model. We've got 10 different testing scores. And now I want to find out the average testing score and the standard deviation of testing scores. Right, you can ignore standard deviation. That's a little technical, but you can look at average score, and the average is 88.759579%. So next time anybody asks you that, hey, what is the performance of my linear regression model? So you will no longer say that, hey, it is 89.47%, but you would rather say that, okay, the cross validation accuracy or the cross validation R squared of my linear regression model is 88.579% because this is a more robust number. Because see, sometimes the accuracies can be very high. Fluke chance, right? I told you, because if the question paper is easy, in some splits it is getting 96%, in some splits it is giving 81%. So there is huge variation, but we're taking at the average. Okay, so this is the idea behind what we refer to as cross validation. So these are all different concepts that we are discussing, which will be very similar to every single aspect of the course that we are talking about. So a lot of core ideas we have covered. We talked about machine learning life cycle. We talked about train test split. We talked about overfitting, underfitting. We talked about the idea of building models. What is fit? What is predict? And now we are talking about cross validation. These are all core ideas. So next time, even when we apply a different algorithm, even when we go to deep learning, even when we do classification, because for classification we have different algorithms that we will use, these core ideas will remain very, very similar. Okay, so just keep this at the back of your mind. This is a model evaluation technique. Okay, this is not an algorithm, but what is this? This is actually a model evaluation technique. It gives me a more robust way to evaluate the performance of a model. Okay, it's not evaluating based on a single number, but I'm evaluating based on 10 different numbers and taking the average. Okay, so that's the idea. Rest, I think there are some other samples that I have done. You can go over the other parts of the code. A lot of things I've done in this notebook. Not all of it is important or relevant right now. Okay, but some of the other things that I've demonstrated here are pre-processing tasks. For example, you can see this one. So this is a very interesting piece of code that I've shared, which we will use later. So here I have used something called a pipeline, right? So what is a pipeline? A pipeline is basically a, a series of different steps that we are applying. So for example, we have a sales prediction problem. It's a regression problem, right? So the sales prediction problem is ultimately a regression problem. Now, what we want to do here is we want to effectively apply a pipeline. So first, we want to do standard scalar. We want to scale the data, and then we want to do linear regression. So we are effectively framing the problem in two steps. Okay, so can you see what we are doing? We are basically framing the problem in two steps right now. So first, we are applying a linear standard scalar. Standard scalar is like a scaling technique. Okay, so some of you who have you can think of standard scalar as like a scaling technique. So first we are applying standard scalar. We are scaling the data. So we are converting all the data to the same scales. And what is it? See, because different values can be in different scales, right? So some values can be, you know, imagine if you look at experience and salary. Think of that use case. Think of experience and salary as the two use cases. So some values can be very high and some values can be very small, right? So if you think of the same, experience and salary kind of use case, so we can have a scenario where the experience of a person usually will be very the experience of a person usually will be very small, right? It will be either from 1 year to 50 years, like that. Experience will range from something like 1 to 50, right? Not more than that. But the salary of a person will typically range from salary of a person might typically range all the way from 1 to 100,000, 100 million, $10 million, whatever. So the salary will be ranging over a larger range. So what you want to do, what we really want to achieve here is we want to go and convert our data into the same scales. And sometimes we have seen it is better on the algorithms, it's better on the models. The models tend to be better, they tend to be more robust, they perform well when we scale the data. So just remember, as a standard practice, whenever we apply any of the models in our case studies going forward, we will always try to make it a point to scale the data. It's a good practice. And then we will apply the algorithm. That is what the pipeline will do. So this is what we call a pre-processing stage. Okay, so when we say data pre-processing means that before you apply the models, before you apply the different models, you will first pre-process the data, right? So first you will pre-process the data, and then you will apply the different models. So these are the two phases that we are talking about. So first step we will go and pre-process the data, and then we are applying the different models here. So that's the way. Okay. This is what we did in the pipeline. So there are these are called steps in a pipeline. This is step one. You can see this is the pipeline, and the pipeline basically has two steps, right? So again, you have the pipeline, and this particular pipeline, there are two steps in the pipeline, and you can clearly see the first step is standard scalar. This is a step name. You can give any variable name. This is a step name, and this is what the step is supposed to do, the step class. And this is the second variable name, LR. You can give any variable name, and this is a step class, which is linear regression. So pipeline can consist of multiple steps. And if you want to see a sample pipeline, you can actually see build a. I mean, I can run the code. I mean, we already seen these things, right? So pretty simple. And now you can use Gemini because we have this in the context. We can say build a complex pipeline consisting of multiple pre-processing. Just to show you an example of how a pipeline looks like, multiple pre-processing steps and ending with a linear regression model. You'll see that when the pipeline gets built, initially you will have multiple pre-processing steps. It will do everything for me. And here we did multiple things, like we have standard scalar, we did something called power transformer. And power transformer is basically used to normalize the data. It's another kind of transformation, and then linear regression. So see, this is how the pipeline looks like. So define the pipeline with multiple pre-processing steps. So we're first taking the data, we're first scaling it, we're transforming it. This is like a normalization technique, and then we are applying the algorithm. Rest of the part is exactly the same: train, test, split, dot fit, and then dot score. Okay, so this is the simple way. I think there's a lot of commenting that is done, but I don't think there's anything complex about this pipeline. Very simple, but you can go and add some more detail, consisting of multiple pre-processing steps, feature selection steps. If you want to really see a complex pipeline, and ending with linear regression model, build a complex. No, so the more details that you make it, the better your thing will be. And maybe if I do it this way, I'll get a more detailed pipeline. This is a very, very complex one. So here, what we have done is we have actually got two pipelines. So can you see? So this is a pre-processor pipeline, and this pipeline is used in this pipeline. So this is again, it's one of the magics of Python, where we can kind of it's like divide and conquer. So you create one pipeline that will only do the pre-processing, and then you will use the pre-processor pipeline inside another major pipeline. So first you are pre-processing, then you are doing feature selection, then you are doing linear regression. So this is how you will build your workflows going forward, right? But I hope you get the ideas. What we are trying to do in these trainings is we are trying to get the idea. What is it? What are the core concepts? So next time you see a code like this, you know what is it? You know the relationship. Okay, so we are just trying to build these spatial relationships in the human brain so that we understand this is this, this is this, this is this. So once you know that, you can build literally everything. Okay. So now moving on, I think these are some demos on pipelines that we have done. You can go over it. And the last part that I wanted to talk about in the towards the end is this thing. Okay, I was explaining about estimators, and remember, this n estimators is typically called the hyperparameter. Okay, so I've already covered this up, but just to briefly recap this idea, this is called a hyperparameter. What is it called? It's called a hyperparameter. So this is called a hyperparameter. That's what you're able to see on the screen right now. Okay. So we try different values of estimators. So along the x-axis, you have something called estimators. Along the y-axis, you have something called score. Okay, so x-axis, you have something called estimators. Y-axis, you have something called score. So we try different values of estimators, and we build different models, and we see which model is giving us the best accuracy. So we can clearly see that as the estimator's value is less, and I think I already demoed that some time back, you see that when the estimator's value is equal to 1, the model is significantly underfitting. You see the training and testing scores are both very low. In fact, we call it the cross-validation score. We discussed about that. What is the cross-validation score? So we can see the training and cross-validation scores are very low when the estimators is equal to 1. And as the estimators increases, the training and cross-validation scores are both going up. So as the estimators increases, as we have more and more estimators, as the as we increase the value of the tuning knob, you can see that the training and the validation scores both tend to increase. So the training and testing scores both tend to increase as the estimators are going up. And this is the graph that we discussed, underfitting here, overfitting here. And we are trying to find out the good fit zone somewhere here. Okay, usually the graph, if you go further enough, you will see something like this. So if I use a different color, the blue is the validation score, the testing score. The testing score will usually tend to drop. The testing score will usually tend to drop. And after a while, the training score will continue increasing. This is the orange. The training score will keep going like this. This is the pattern we'll generally see. Right. So as you increase the estimators beyond the point, the training will touch 100% and it will remain there, but the testing will tend to drop. And you're typically trying to find the sweet spot, which is somewhere here. This is the good fit that you're trying to find. But remember, overfitting, underfitting, and good fit are very relative concepts. So we will never say that we have a perfectly overfit model, a perfectly underfit model, a perfectly good fit model, but we will always make relative comparisons. We'll always say that, hey, this model is more overfit, this model is more underfit, and this model is more good fit. We'll always make a, you know, we'll always go and make relative comparisons. So this is a very simple demo, and I hope this gives us a very good understanding with respect to what we are doing in linear regression at a very high level. And we also managed to see a lot of general machine learning concepts as part of this conversation. And from here, we'll go to a lot of case studies we will do. We will continue the conversation forward. And we will start off with our very first case study. And we can continue this conversation in the next session.